And
Indeed,
so,
me too, of course, but still, you know, and going to Antarctica is as tricky as you can get, but still
yeah,
things are going to be a little crazy with
you might
travel.
kill all those penguins.
We did a dozen PCR tests in the span of a week and a half.
Oh my goodness. And I take it none of them were positive.
No. And actually, we heard this afterward. You know, there were two cruises, and in fact, Jay Pasikoff, Michael Zeiler, and a couple of other people were on one of the cruises that had to turn around because 4 crew tested positive. After we got down there and saw the eclipse, we heard that if anyone on our plane had tested positive, they would have turned the plane around.
Yeah.
So that, luckily that didn't happen, but we had been tested, you know, 10 days before that, you know, every day.
That's, well, we've all been living under conditions that have been diabolical. So,
yeah.
And it was certainly the year from hell for the B&B, because we would sell out and then have to cancel everybody. They wouldn't allow them to travel.
Oh boy.
And so we'd fill it up again, and then forest fires broke out and they wouldn't let them travel. And so we canceled all of them again, and it was over and over again. And so we just, as I said, we were 40% down, and normally we're sold out every year, 20 years. And that's, as I said that we put 20,000 people through the B&B, which I mentioned.
That's amazing, Jack. That's incredible. Well, let's hope, you know, late this year we get some traction, and Omicron is the last big spike, and its lack of severity leads to, you know, less serious illness and more of the 38% of the non-believers that they actually get vaxxed.
So you're coming live in about 10 minutes, is it?
Yeah, I think we're actually live now. If anyone's on early looking at us now, they can probably hear us, I think.
Yeah.
But I think we have about 6 minutes to go until Scott, I think, starts things up, I believe.
Yeah.
Which is usually right on the hour.
Make some notes, because this is the only second one that I've done.
Yeah.
And don't know what in the hell I'm doing, so.
I don't believe that for a second, Jack.
Well, I can tell some pretty funny stories and keep them clean, so.
Yes. If there's a non-broadcasted star party at some point, we can push the boundary a little more.
No, I'm pretty conservative, actually.
Yeah.
But Alice could come on. She's the Irma Bombeck of the astronomy village here.
Indeed, yes.
Well, I'm going to go and make some notes. So you'll lose me for a few minutes here.
All right, we'll see you in a minute. How are you doing, Conal?
I'm doing great, David. How about yourself?
Good, hanging in there. There's a lot going on. We have yesterday we went back into the office for the first time in 2 years.
That's fantastic news.
So that was an odd circumstance, and we're in 3 days and at home 2 days from now on, so they say.
And I take it all as well so far?
Yeah.
Good. Well, on my end, we just got our first clear skies in probably about 2 weeks. So I got out to see the moon, Saturn, Jupiter.
Excellent.
They've been putting on quite a show the past month or so, and I finally got to take some images. So hopefully I'll share some of those later.
Well, good. Oh, that's good to hear. Yeah, it's always makes you feel a little more settled and a little better after a cloudy period to see the sky again.
I agree. You know, something you can count on there.
Yeah.
So I'm putting together a little bit of a slideshow now. I wondered what images I have that had some relevance to cosmic dust. So I figured some Milky Way shots would be nice, things of that nature.
Yeah. There's a whole lot of dust in the Milky Way and even in the solar system.
Sure. The zodiacal light as well.
Exactly. Yes, the zodiacal dust.
I had an opportunity to see that just once. I was at Cherry Springs State Park a couple of, what was that, 2018?
Mm-hmm.
And I caught it in the middle of the summer. And I think they say it's better in the spring and autumn.
Yeah.
But that was just a stunning sight to see, you know, something you don't see too often from many other skies.
No, and that's a pretty dark sight for the eastern U.S. And of course, you have to have a really nice dark sky to see the zodiacal light, especially as a kind of a wedge, you know, that goes up.
Yeah, that's kind of what it looked like to me. And I mean, I'd never been to a dark sky site before. That was my first time. So it might have been a couple of hours after sunset and there's still that light on the horizon. So
yes.
I had some questions and, you know, it was kind of a nice light bulb moment, but that was awesome
Indeed.
to see.
Yeah. It's pretty cool that you can see light scattered off of that dust.
Mm-hmm. Heard there were some papers recently. I think this was maybe a year or two ago. I read this, that some of that dust was coming from Mars. It wasn't just drifting from the asteroid belt or the early solar system. I think there was some weather factoring in there. The sun blew off some of the atmosphere with dust included.
There you go.
Something along those lines.
Yep. Hi, David. How are you?
Hello there, David. Welcome back from Antarctica.
Well, thank you. I survived barely, but I'm back.
Yeah, I heard your little speech last week, and I'm glad you're back safely.
Well, thank you.
We have another guest here today. You can see his face in the back there. It's Ed Gunther.
Hi, guys.
He's
Hello.
with us today. He's going to say a couple of things. And it's good to be here. I'm not going to be here for very long today because we have to go out, but I am here for now. Hello, Conal.
Hey, good evening. How are you?
Fine, thank you.
So you said you're going out. Is that, I take it for observing?
Yeah,
there'll be some observing.
We're mostly going out to meet some friends for dinner.
Oh, have fun.
Thank you. Hi, Adrian.
Good evening, David. Just stopping in quickly. About to have a little dinner and listen in on the presentation. It's good to see you again.
Well, thank you, Adrian. I want you to meet Ed Gunther.
Hi, Adrian.
You can see half of them.
I'm over here. There we are.
Yeah. Good evening.
Yeah, Adrian, I didn't see the bowl game the other day. How'd you guys do?
We did not do very well.
Oh, I'm sorry to hear that.
Georgia showed up and our team didn't, but it was still a good run.
There you go. There it is.
So Penn State did well.
Yeah.
Conal School, you guys got by. Oh wait, I thought you guys got by Arkansas. I could be mistaken.
I think we did. I didn't follow it as closely.
For a while it looked like it. Yeah, Conal, did you guys get by Arkansas?
I think so. I can't remember. The last news I saw was about the bowl game. Everyone was debating, do we want to go on the side of a Big Ten school or do we want Georgia to beat our rival Michigan? Like, no one really knew what to say there.
Right.
But
No.
The outcome was what it was.
Yes. And
about 2 or 3 times a century, a massive star in our galaxy
looks like we're starting,
explodes.
so we'll carry on.
The star's
later.
core may survive as a neutron star or a black hole, but the rest of it rushes into space as swiftly expanding debris behind a powerful shockwave. As the supernova remnant grows, it sweeps up interstellar gas and gradually decelerates. Yet even thousands of years later, its imprint on the galaxy remains impressive. Exploding stars and their remnants have long been suspected of producing cosmic rays, some of the fastest matter in the universe. Where and how these protons, electrons, and atomic nuclei are boosted to such high speeds has been an enduring mystery. Now, observations of 2 supernova remnants by NASA's Fermi Gamma Ray Space Telescope provide new insights. Because cosmic rays carry electric charge, their direction changes as they travel through magnetic fields. By the time the particles reach us, their paths are completely scrambled. We can't trace them back to their sources. So scientists must locate their origins by indirect means, which is where Fermi comes in. The interaction of high-energy particles with light and ordinary matter can produce gamma rays, the most powerful form of light. Unlike cosmic rays, gamma rays travel to us straight from their sources. In 1949, physicist Enrico Fermi worked out how what he called magnetized clouds could accelerate cosmic rays. Later studies showed that a variant of his method, called Fermi acceleration, worked especially well in supernova remnants. Confined by a magnetic field, high-energy particles move around randomly. Sometimes they cross the shock wave. With each round trip, they gain about 1% of their original energy. After dozens to hundreds of crossings, the particle is moving near the speed of light and is finally able to escape. If the supernova remnant resides near a dense molecular cloud, some of those escaping cosmic rays may strike the gas and produce gamma rays. But electrons and protons make gamma rays in different ways. Cosmic ray electrons do so when they're deflected by passing near the nucleus of an atom. Accelerated protons may collide with an ordinary proton and produce a short-lived particle called a neutral pion. These pions quickly decay into a pair of gamma rays. At their brightest, both types of emission look very similar. Only with sensitive measurements at lower gamma ray energies can scientists determine which process is responsible. Now, Fermi observations have done just that. They conclusively show these supernova remnants are accelerating protons. When they strike protons in nearby molecular clouds, they produce pions, and ultimately, the gamma ray emission Fermi sees. NASA's Fermi has detected gamma rays from many more supernova remnants, but the jury is still out on whether accelerated protons are always responsible and what their maximum energies may be. Nevertheless, the Fermi team has taken a major step, a century after the discovery of cosmic rays, in establishing just where they arise. Something that would satisfy, but certainly not surprise, the original Fermi.
Well, hello, everyone, and welcome to the 79th Global Star Party. I'm Scott Roberts from Explore Scientific and the Explore Alliance, and we have an incredible lineup of speakers for you, as always. Starting off every Global Star Party, and I'm going to get started kind of quickly here because we have David Levy, who has to get out quickly, but he did sacrifice and make the time to be with us at the first part of the Global Star Party. David, I want to turn this over to you, but thank you for being so wonderful to sacrifice and make this appearance.
Well, thank you, Scott. And it's good to be here. Before I do my poetic quotation for the day, I'd like to introduce my friend Ed Dunford. He is one of the regulars at our Adirondack Astronomy Retreat, and he and his wife, Wendy Gordon, are visiting us. And so, Ed, would you like to say hello to everyone?
Hi, everybody from Tucson. I live just south of Montreal, so I have really questionable skies this time of year. We do what we can to view, but I've been out here for a week, and I just had some eye repair done, and I'm actually seeing things that I've never seen before while I'm out here in the nice clear skies. So I'm loving Tucson a lot, and I'm always happy to be part of the star parties here. So. And on my birthday this year, I saw 2 supernova remnants for the first time, and Mercury, which for some reason in 55 years of trying, I've never been able to see. And we're seeing it naked eye here tonight and loving every minute of it. So thanks for having me.
Well, thank you, Ed. And for my poetical quotation today, usually around this time of year, I head off to Whitehorse in the Yukon Territory in Canada for the Aurora 360. But it appears that that's going to be postponed this year because of the apparently never-ending pandemic. But anyway, my poetic quote is going to come from someone who visited Whitehorse. Robert W. Service was working on a poem at the time about a fellow from Plumtree, Tennessee, who really wanted to go up to the Klondike to search for gold, but he was worried about the cold. And he told his people he doesn't think he's going to make it. It's just too plain cold. And he says, I want you to promise me, if I don't make it, you are going to cremate me. And the speaker of the poem says, okay, I will. And then, of course, he dies. And here it goes. He finally finds a place at at a lake in the Klondike, and he decides to build a crematorium. And I'm going to quote to you now the last three verses of the cremation of Sam McGee. And I think you'll find this fun because it's one of my favorite poems. And I believe it is the favorite poem of almost every Canadian. And it goes like this. I do not know how long in the snow I wrestled with grisly fear, but the stars came out and they danced about. Here again, I ventured near. I was sick with dread, but I bravely said, I'll just take a look inside. I guess he's cooked, and it's time I've looked. Then the door I opened wide. And there sat Sam looking cool and calm in the heart of the furnace roar. And he wore a smile you could see a mile. And he said, please close that door. It's fine in here, but I greatly fear you'll let in the cold and storm. Since I left Plumtree down in Tennessee, it's the first time I've been warm. There are strange things done in the midnight sun by the men who moil for gold. The Arctic trails have their secret tales that will make your blood run cold. The northern lights have seen queer sights, but the queerest they ever did see was that night on the marge of Lac La Barge. I cremated Sam McGee. Thank you, and back to you, Scotty.
That is awesome. That's the first time I've ever heard that poem, and it seems like you've got that poem in memory. I didn't even see you looking down really at the last part of that, those verses. So
my uncle knew the entire poem by heart, and he recited it one night for us. It's a wonderful story.
It's awesome. I really love it. I love it. So you guys are off, David, and again, thank you for coming on, Ed. You know, I know I see you sometimes watching our programs and stuff, so it's fun to see you on the other side of the camera and in the broadcast. So, and I'm glad that your eyesight is, you know, doing so well. It's wonderful.
You can collimate your eyes, Scott. It turns out my eyes were uncollimated. Now they're collimated.
They're out of collimation.
Yeah, it was out of collimation. So there's a talk in there somewhere.
That's awesome. Well, I hope to see you also at the Arizona Dark Sky Star Party. Ed, you were at the last one, and you know, we're still planning on that event in Oracle, Arizona. So
excellent.
All right. Okay. So our next speaker is Dave Eicher. Dave is the editor-in-chief of Astronomy magazine. He is, if you had tuned in a little bit early and heard some of the chatter back and forth, you would have heard about the first time that David Eicher had met Jack Newton, who's going to be on our program. Jack was, you know, an admirer of the young David Eicher, as well as David was pointing out that Jack is one of his heroes. We got to also hear a little bit of what it was like to be down in Antarctica to see the eclipse. We were so lucky to have David Eicher on so many global star parties. I really appreciate you coming on as often as you do, David. It's great. So I'm going to turn it over to you, and thanks again.
Thank you very much, Scott. It's an honor to be here as always. And I will see if I can share my screen and share a tale of a very cold place. One of the few places that I know of that's colder than Milwaukee. All right, let's see here.
Or Detroit.
Can you? Yes.
Yeah. Okay.
Can you see me standing there with my parka open to take a quick picture before I zip it all up again?
Yes.
Okay. Well, I had the chance to go along with some magazine readers and other folks down to see the eclipse on December 4th. It was a total solar eclipse, visible only from Antarctica. And it was a real adventure. And I went down in order to write a story for the magazine. It'll be upcoming in Astronomy magazine in a couple of issues. So I thought I would share a little bit of this before I get back into some mineralogy in the ensuing weeks for a little while here. And as you can see, Antarctica is a very icy place. It's very cold. And we had 24/7 sunshine, except for the eclipse itself when we were there, of course, it's the summertime in Antarctica. So it was as balmy as it gets. And I'll talk about sort of the details and what it was like, but it was a real adventure. And not to, steal a word from Shackleton, if you've done any reading about Antarctic journeys and adventures, but it was a little bit of an endurance. I've been to very, very cold football games for 4 or 5 hours, outside, and then during the game. This was being here under these conditions for a week. We were on the ice for a week. And it was a tremendously complicated thing because of COVID-19, of course, to get down there and spend a few days on either side of the trip itself in Antarctica in Chile. So I'll tell you a little bit about what that was like. And we did it all for 46 seconds of totality, which we saw beautifully. As happens at most all eclipses, the eclipse gods can, torment you a little bit. And it was, photometrically clear in Antarctica the whole time, basically. And then the morning before the eclipse, about a day and a half before the actual eclipse, we woke up and it was socked in entirely, just clouded over completely. So, but fortunately, by the morning of the day on which we did our eclipse adventure, into the early morning again, it had cleared again, and it was beautiful and essentially photometric. So we had a great view of the eclipse. It was a fancy thing to go down there, and I'll explain why a little bit. A lot of people have gone to Antarctica via ship. And tragically, some of our eclipse expert friends were on shipboard, and they had a few people on the crew test positive, so they turned around and didn't see it. There was a huge amount of paperwork that the Chilean government required of us to get down. We went to Chile, as I mentioned, first, and then to a portion of Antarctica that's governed by Chile. So for me, it was Milwaukee to Houston to Santiago to Punta Arenas to Antarctica. So it was about almost a full day on planes, not including the time between planes and doing testing and so on. We had daily PCR testing also on the plane and on arrival when we got there, and obviously before we boarded and so on, both in the United States and in Chile. So we had about a dozen tests altogether, and we had all of our folks test negatively, which was nice. We had a group of about 50 people altogether going with us in our group. Instead of taking a rickety Russian transport plane, which has been done to Antarctica many times, usually successfully, but not always, we landed a Boeing 757 on the ice. And so we went to a place that's called Union Glacier Camp, and it's about midway between the coast and the South Pole. It's a large sheet of ice. We were still about 600 miles from the South Pole where we were, but we landed on a blue ice runway that was about 4 miles long. And this has only happened with a Boeing like this for about 6 years now. So it's a pretty new capability to land a major plane, commercial plane on a runway right on the ice. As I mentioned, we had daylight the whole time. It was only darker for the eclipse itself. It was warm for Antarctica. The average temperature in our camp, which was pretty calm and pretty warm feeling because the wind was not too bad usually in our campsite. It was about -5 to about 10 degrees, sometimes up a tad over 15 degrees. But icy wind chills. So when you went on expeditions each day, what do you do when you're in Antarctica for a week, aside from a 46-second eclipse one morning? Well, you go and you do expeditions in various places, and I'll show some photos of what we did here and there. And going up to higher elevation and in vehicles that took us up on tracks or on heavy tires to see some of the mountains and some of the rocky areas and explore a bit, it felt much, much colder because the winds whipped up, and we had wind chills that were down to in the sort of -35 or -40 range. So you had to have a serious checklist of approved clothing, multiple layers of socks, of pants, of undergear, of multi-layers of fleece and of down, and then a very heavy parka, and of course a hat and a buff and goggles that go over your glasses, and everything pulled up to cover every part of you, and heavy parka boots, heavy winter boots as well over everything. So you had to be really, really wrapped up in order to go, which thankfully we were. But even, when we went up into the mountains, tiny little bits of skin, between your goggles and your buff, it just had a biting, icy wind on them. So it was, you almost felt like you could imagine what it would be like. And some of our guides actually had been here. They said, this is kind of what it's like being at Everest Base Camp, just a little sort of taste of that. So it was an interesting challenge. We followed the traces of some explorers who actually were close to where we stayed in Punta Arenas, including Robert Scott and Amundsen and Shackleton, as I mentioned. I mentioned the heavy clothing that we had. We had 2-person tents camping on the glacier there. And of course, as you're driving around in these vehicles, you have to drive along certain routes that have been marked with flags so that they've been checked with sonar to make sure that the ice is stable. So you don't all of a sudden have a crevasse open up and that kind of ruins your whole week. So it's really an adventure, and you have to be very careful here. You have daily meals in a communal tent, if you will. It's a bathroom facilities and regulations. It's quite heavily regulated, and we had a shower at most every 2 to 3 days. And what you did for the shower in Antarctica was to fill up a bucket with scalding, boiling water that came out of a faucet, because there was a snow melting machine that produced this incredibly hot water. Then you had to shovel snow into it to mix it to a temperature that wouldn't kill you. And then you put the bucket into a pump hose, got into the shower, and you had the best 3 minutes a couple times of that whole week, because after a couple days in Antarctica, you're filthy, so that shower was like being reborn. It was amazing. And you had to be very careful. You can't leave anything in Antarctica. You can't contaminate anything. There was no life there at all where we were, except for the human beings and microbes, of course. But there were no penguins. There were no polar bears. There was no nothing where we were. That stuff is all much closer to the coast. So you have to be very, very careful not to pollute or contaminate the environment. So that means doing something like taking a pee bottle along with you in case you need it on what is a 4-hour expedition, say. So you learn to regulate your drinking and your fluid intake and your hydration, really such that you have to make a deposit with some fluid only when you're back in camp. So these things you kind of pick up and learn as a kind of a roughing it. Well, there were a bunch of interesting areas that we went to near our camp, driving several miles away. And so we had sometimes a half hour, 45-minute drive in a tracked vehicle or in a heavy van with big, heavy rubber tires. That took us to a few places that I'll show you some brief pictures of. The Drake Icefall, the Charles Peak Wind Scoop, Rhodes Bluff, and the Buchanan Hills, which were interesting for different reasons here. So this was the first view that we had of Antarctica. I shot this outside the plane as we saw Antarctica and the mountains on the coast with my Android phone. This was shot. So this is kind of, wow, you're all of a sudden, you know, there's no turning back. Now you're coming into Antarctica here. Pretty impressive. And you don't realize there's a tremendous amount of topography and very high elevation mountains in places on the continent. Here, if this works, I will show you this, and forgive me, it goes on a little bit, but this is our plane landing on this blue ice runway.
Amazing.
So do you know if you have to be a specially licensed pilot in order to be able to do this?
You do.
I would imagine
These
you
flights
have to
are
be.
only run at certain times and only by, of all things, Icelandic Airways, believe it or not. And you can see that it takes you quite a distance to stop.
How thick is the ice?
Even with the thrust reversers on, you have a long ride on the ice to stop the plane there, you know, with the mass of that plane. Sorry, Jack, did you have a question or a comment?
How thick was the ice? You know?
It's something on the order of 3 kilometers thick.
Oh, wow.
Wow.
So it's pretty thick, but you can get cracks and crevasses that could be major trouble, even for something as light as a tracked vehicle. So you need to be careful there. Oh, we don't want that. There we go. Okay, so now we're properly dressed and we're going out into a slightly higher elevation area away from camp. And you can see that wind erosion on the glacier. Now you're on Union Glacier, which, you know, is moving, but it's moving so slowly that you don't notice it at all, of course. But you're on a glacier, camping and walking around and doing all these things. So you can see that wind erosion makes these little scallops on the very hard ice. And the temperature here was probably about 0 or so, not incredibly cold, but windy. And you have it, you know, on your boots, they have these little things. They're not really crampons, but they're called micro spikes that the guides put on you that are little razor-like spikes. And you have a ski pole too. So you can kind of navigate around and you don't go flat on your back and hit your head, you know, into something that's like concrete. So that was a bit of a challenge, just getting used to walking around on this surface. And this is one of the areas where ice comes over the glacier and contributes to the glacier itself here. This was inside the tent. You have a 2-person tent, and you can see the accommodations here. You know, it's 24/7 daylight, as I mentioned, and you have this very heavy sleeping bag that is a 2-layer thing. It's a bag inside a bag, and then you have a hood that's heavy that pulls up over your head, and another thing that pulls up over your buff. So you can get in this thing and have only your end of your nose and your mouth exposed at all. And on the colder days, it was cold in this tent. But on the warmer days, when it was up, between 15 and 20 degrees Fahrenheit, maybe for a little while, you felt pretty nice and warm inside that bag, with your underlayer of clothes on. So, but it's pretty primitive there, and you can see, and you have this and bathroom and shower and dining facilities, and then a little place where you can give some talks and a library, and that's about all you have at the camp here. Well, the Charles Peak Wind Scoop was a place where we went, and as you can guess, probably there's a mountain here off to the left where the wind often whips down and pushes helps to push the glacier and the currents off of a part of the ice. And a couple of weeks before we were here, it was so warm that the guide said, where we were walking on this little frozen pond, if you will, that there was a little bit of a trickle of water, which is unusual there. Here's also the wind scoop, and you can see this incredible sedimentary rock here. The rocks in Antarctica vary a good bit. There's a little bit of volcanism and basalt, but there's a lot of sort of granite, and quartzite and gneiss and other sort of dense rocks, and some of them even actually holding fossils because, long ago, the continent was part of Gondwana land, so there is a fossil stuff. And unfortunately, I desperately looked around for meteorites here, which you're not supposed to take according to the National Science Foundation. But as you can see here, there were fields, this is about 3 feet across, there were fields of about 1 trillion rocks that you could walk across, and I didn't find any really obvious meteorites with effusion crusts. But, you picked up some interesting things and the guides said, take it, so the rules were a little flexible. This is also the wind scoop here, and you can see some evidence here in the smaller piece that's on the big rock here of some fossil action. I don't know what they are, actually. I'm not a big fossil guy, unlike minerals and meteorites, but there are fossils that you can kind of abundantly see in this rock that's quite a number of million years old. There's a self-portrait here that somebody shot of me. This is the so-called Drake Icefall. This behind me, it's about a 4-kilometer long ridge of ice that comes off of a mountain and contributes to the glacier and pushes the glacier ahead. And one thing that was really interesting, the atmosphere was so incredibly clear and bright, and the incredible to breathe. And I think some other people kind of said this to me. I got the best sleep I've ever had, I think. And I slept like 10 and 11 hours a night when I was there, which was really refreshing, even though it was cold. But it was also played some tricks on you. You could look across, there was a prominent mountain near our camp, and it looked like, well, I could walk right over there and walk back, and it was 4 kilometers away. So the distance scale is deceiving a little bit because of the clarity of things there in Antarctica. This is a famous rock near our camp that's called Elephant Head, that is a kind of a hardened marble and quartzite. And it's been studied because it's permafrost, and that is that a certain amount of glacier below the rock even is always in permafrost. And Chris McKay, who's you may have heard of or know, he's a good pal. He's a Martian scientist for JPL, and he's written an important paper about this actual rock being an analog, how there could be a permafrost of the same temperature on Mars. And the same sort of composition. So the sort of survival of microbes at certain depths in and around and below this rock could perhaps tell us something about microbial life in permafrost on Mars. You can look up that Chris McKay paper if you'd like to. This is the Rhodes Bluff, where it's a little deceiving here. This is all wide angle stuff. But if you go up to this kind of ridge of rock here at the top where there's some mist coming over there, some ice particles coming over, there's a huge fall off that goes into the glacier over this ridge. So the guide said, you know what, if you go over the top of this, you're going to go down about 5 kilometers and be killed. So don't do that. So, okay, we went up and we took some pictures here, but we didn't do that. So that we took that warning seriously. But this was another place where it was extremely cold and very, very windy up in this area. And we're up at pretty decent elevation here. This is another area where we explored lots of rock and so on, the Buchanan Hills. That was a similar place, and it was very, very windy, and you had almost a sort of an imagining of what it would be like to start off at the lower elevation of a place like Everest when you were up in the winds whipping around in mountains like this. It was quite an adventure. And this is the group shot showing the folks who traveled with us here that we took on Eclipse Day after the eclipse. And then this is my shot after I lectured everyone all week not to take any pictures of an eclipse, because why? As Norm Sperling and Michael Bakich and others always say, afterward, every eclipse lasts 8 seconds. Don't waste your time taking a picture. Well, then I did take a few pictures though. And this is my shot just with a Canon 6D of the eclipse handheld. During the 46 seconds. And you can see we were not right at the center line, and the eclipse was brief, and the ice was very reflective. We saw the most incredible shadow bands we'll ever see in our lives, I'm sure, on the ice, and longest lasting. It was really remarkable. But the sky wasn't all that dark. And I don't know if you can see, but Mercury is just to the right and just slightly above the sun there, and then Venus much brighter is over near the right-hand margin there. But this was our eclipse site, and basically how totality looked. And fortunately, we had a beautiful photometric sky when push came to shove, actually. And these are some shots that were taken at our site telescopically here. And of course, we're all looking forward to the next big eclipse where we don't have to go very far at all, especially if you live near Carbondale, Illinois, and saw the 2017 eclipse there. You could also step outside your house in 2024 and see totality there again at the intersection of those eclipses. But so let's look forward and hope that we have good weather in the United States for 2024. So that's sort of my brief introduction to Antarctica. I really enjoyed it. Having gone to Antarctica once, though, that's enough. I think no need to go back now. So
You're not.
Wisconsin is cold enough for me.
I'm curious, when you guys deplane, I mean, you're getting off this 757, okay? You must have just had like stairs that you were going down. How did they get you off the plane? Were there some people waiting for you, or?
Believe it or not, we suited up in large part to get on the plane, because once you get off, it was cold as hell and it was windy on that airstrip on the runway. And the ice, we had no spikes on or anything. So it was really slippery. And they told you, they helped you off down off an exit ramp, off the plane, exiting out of the rear of the plane, helped you off and stabilized you and said, watch it, this is really slippery, and kind of helped you to get over to a tracked vehicle that would then take us to the camp, because, people were going to go head over heels on this because the runway has to be very smooth, to safely land on. So it was like slick glass.
Oh my God.
So they warned us very carefully and
So there was no baggage claim or like little restaurant you could hit.
The baggage was all taken care of, and there's a staff. There were about 50. There were some people, believe it or not, from Madison Square Garden of all places. Also about 8 or 10 people there who were doing a film about the camp and the eclipse for whenever. So there were maybe about 60 people or so altogether in camp, and then a staff probably maybe of about 25 or 30 So there
wow.
were plentiful staff people to kind of help us get where we're going. So they took all the bags and everything and dropped them right at our tents.
David, what was it like leaving on that ice runway?
It was nice because when you're in Antarctica for a week, no offense, Antarctica. And for me, it was the seventh continent. So I was really fortunate and glad to be able to go on an adventure. After a week of this temperature and the adventures we went, I was glad to get the hell out of there. Frankly, it was really nice to get onto the plane and head back towards some kind
I
of.
assume they had to use most of that 4 mile long runway to get.
Yeah, they went for a while before we were wheels up, certainly. But a 757's engines, have a lot of burst too. So they sort of gun it, taking off from there. Yeah.
Excellent.
So the plane.
It was about a 4-hour flight from Punta Arenas. So maybe about just a little over 2 hours. You are just seeing the ocean from Chile, and then for a couple hours you're flying over Antarctica before you land, and vice versa.
Amazing. It's amazing. Thank you for taking us down there. And I got to do it from the warmth of my own office here in
That's
Arkansas.
A little better in that respect. Yeah. Thanks, Scott.
That is awesome. Thank you, David.
Thank you.
Great. Okay. So we are going to now move over to Carroll Orge and the Astronomical League. I do like to point out that, if this is your first time to watch Global Star Party, you're watching a great one right now. This is, we've got, an incredible lineup of speakers tonight, but the Astronomical League is perhaps one of the world's most important organizations in the whole, astronomical community, be it amateur or professional. The league has 75 years of history. It has included among its members some of the most iconic astronomers worldwide. It has some amazing observing programs, recognition awards. I might have mentioned this a little bit earlier, but they have like over 300 clubs that belong in this massive federation that is the Astronomical League, and somewhere in the neighborhood of 20,000 members. If you are looking for a way to enrich your astronomical experience, I can recommend nothing more than to join the Astronomical League, either as a member at large or to join an Astronomical League club. And so I'll turn this over to Carroll. Carroll and the Astronomical League have been on almost all of the global star parties, and it's been a real pleasure. And so, Carroll, thank you very much for coming on to the 79th Global Star Party.
Thank you, Scott. Good to be here on this first Global Star Party of 2022. And thank you for your continuing support of the Astronomical League. We couldn't do it without you, Scott. So we appreciate that very much.
Thank you.
I'm going to go ahead and get into our questions, and I'll share my screen here.
There you go.
We're getting there. Hold tight. Okay. The first slide we want to bring up is the warning for if you win a door prize that requires you to look through the eyepiece. We want to make sure you have proper filtering to make sure that you don't look at the sun without some kind of filtering. So that's the one we like to give. From the last star party of 2021, December 28th, we had some questions, and here are the answers. Everybody see that's okay?
Yes.
Okay. True or false? There are more trees on Earth than stars in the Milky Way. And that is true. There are about 3 trillion trees on the earth. I guess someone counted them. And between 100 to 400 billion stars, approximately, in the galaxy. The new catalog was assembled in what year? The answer is, it was assembled in 1888 by J.L.E. Dreyer and expanded on work done by the Herschels. Last question for that last star party. About 12,000 years from now, we will have a new North Star. What is the name of that star? And the answer is Vega. That will be the new North Star, approximately 12,000 years from now. And we had several people get correct answers to the questions from December 28th, several of which are either on this broadcast or who have been on many times. Cameron Gillis, Jason Wallace, Billy Beckett, Andrew Corkell, Rich Kraling, Josh Kovac, Conal Richards, Rich Eubank. I think there's one more here. I guess that's it. And they will be put into the door list prize for later drawings. And now we get to the questions for tonight, for January 4th. And if you know the answers to these, send your answers as quickly as you can to secretary@astroleague.org. Question number 1. What is the name of the tool used by astronauts that combines a pair of pliers and a wrench? Everybody has a couple of those in their toolbox, but what are they called when you're in outer space? The combination of the two. And again, send your answers to secretary@astroleague.org. Number 2, which 4-letter word beginning with N is a star showing a sudden large increase in brightness, then gradually returns to its original state over a period of weeks to years? And again, send your answer to secretary@astroleague.org. And finally, for question number 3, Phonology is the scientific study of which celestial body? And send your answers again to secretary@astroleague.org. Toward the end of the month, on January 21st, which is a Friday, we will be holding our next Astronomical League Live event. And we're still in our 75th year for another few months. Actually, our 75th anniversary occurred in November of 2021. So we've got a few months to go before that year's complete. So we're completing that celebration. We don't have the speakers named yet. However, stay tuned and much more information will be coming. And I think that's about it. And now back to you, Scott.
Okay. All right. So we're going to shuffle a little bit here. We are going to bring on Jack Newton. Jack Newton is in his southern home in out there in near Portal, Arizona. And Jack, he's someone I've known since the early 80s. He is, when I was introduced to Jack, a dear friend named Mark Coco, who worked at Celestron, pointed him out to me and he said, Scott, there is one of the nicest guys you'll meet in the amateur astronomical community. And at that time, Jack had just come out with a new book called I think it was called the Cambridge, or no, it was the Messier Catalog or something like that. Jack will have to remind me what the title of it was, but it was all the Messier objects photographed with an amateur telescope. And that was something that we really didn't have access to before. Most compilations of astrophotographs were done with professional telescopes. And so it was kind of a reality check to see how beautiful and amazing deep sky objects could be made with an amateur instrument. And So, and Mark was right. I got a chance to meet him at the Texas Star Party in 1983. And, after a few years after that, we made a really close friendship, and we've been friends ever since.
Yes.
So Jack, I'm going to turn this over to you, but thank you for all those years of inspiration. And, this is the guy that I often say, if you tell Jack Newton that something can't be done in amateur astronomy, he's going to go out and prove you wrong. He definitely is a guy that breaks the boundaries. So, Jack, I'm going to turn it over to you.
Scott, you're very, very kind. We go back a long, long ways, and I can remember Carstner Caverns Star Party, and I remember asking you, what would you like me to talk on? And he said, I want you to do your history and go back, and I want to hear about Jack Newton and all of the firsts that you've experienced over the years. And because of that, I went back further and further and kept finding newer and more exciting things, and adding to that. And then I thought, well, gee, maybe I should form an astronomy club. And so we've done that, the Newton Astronomy or Astro Club. And Scott was responsible for that. And I must say that not only did I enjoy the talk back then, but it caused me to delve deeper and deeper, and new and more exciting things kept popping up. And
you've done so much, Jack. It must have been difficult to kind of look back, because you're not the kind of guy that does look back. You're always like looking at what you can do next, how you can capture that new supernova or galaxy, so you have so many discoveries, so many things that you've done, including making some of the first color CCD images, helping people back in the film days with a cold camera, and these are just some of the things I know about. There are so many things that you've done, and so many organizations that you've helped over the years. So, it's when you look at it all, I'm really in awe of it. I really am. So,
well, Scotty, all I can say is that you're the best friend I have, I'm sure, and our careers have been intermingled, and we've done just so much together. And gosh, what you've done, you're going to go down in history as one of the most famous skookum astronomy guys that ever walked this planet. And I say that in all sincerity, because wow, what you've done here and opened the world, literally opened the world to astronomy. I can't say enough good things about that.
Thank you. It's very kind, Jack.
What I wanted to do, though, is talk a little bit about dust. I think that's the name of this. And if you go back and look at some of the photographs that we take, and look at the witch head, that being likely the nose, but there you are with a nebula full of dust, and making everything so interesting to photograph. And let me, Scott, can you switch me back, or do I switch back?
Scott, I think you're muted.
Yeah.
I am muted.
Yeah.
I said,
I
there's like a little green button at the bottom of your Zoom platform there. And it says share screen. If you click that, then you'll see the application that you want to share, and you click on that and then commit to it.
Okay, that's the double cluster I've got, but I need to switch back, and you what's the icon look like on my
It's going to look like it just at the very bottom, you're going to see a green share screen button.
Okay. I do not have a shared green button down at the bottom.
I think if you move your mouse to the bottom of the screen,
It may pop up.
those icons may pop up for you.
Yeah.
Okay. If I close this picture off,
Oh, it could be hiding. Yeah, it could be hiding behind one of your other.
the now I've got
Can you see yourself?
I can see myself now, and I've got a share screen green button.
There you go. Click that.
Yeah. Okay. Sorry about that.
No problem.
Obviously,
This happens to all of us. So
yes, but it usually happens to me more often than not. But we do have some examples of some really neat dusty objects here.
oh, there you go. Perfect.
Yeah, there's a shot that I took over the last 12 months, and it's of course the Dumbbell Nebula. And what makes it so interesting is that the interaction of dust and you can see the ionized oxygen, which is your greeny blue color, and then the red, which is taken with your H alpha filter to give you the tremendous detail that you can see. The other things that I wanted really to talk about here was if you take a magnet and if you're young, you get your father to get a ladder up when he's clearing the eaves on the roof and drag that magnet along, and you will collect micrometeorites clung to that magnet, which will show up nicely in either a magnifying glass or even better if you've got a small microscope. And I can guarantee you that you will pick up space dust and on your magnet in about 20 minutes. And that's anywhere on Earth. So have a ball doing that, but do it safely. And I don't want any kids going up on ladders with like I did
Like you did.
when I was a kid. Or I've gotten into an awful lot of trouble.
Yeah.
Now, if I click sharing the screen again,
Okay.
will that, or am I all right what I'm doing?
Yeah, I can do that for you. There we go.
Okay.
All right.
The the other thing, if you are interested in the Astro Club, if you go www.newtonastroclub.com, you can sign up. And this is free, and we'll be doing many stories like what we're doing here on what I've been doing over the years. And I must say that one that just popped to mind because of the Eclipse expeditions. I chartered a DC-3 to take people up to the Northwest Territories, which was just off of Baker Lake. And that was a really exciting trip. And we'll cover that and in detail in the future, or maybe even future talks here. I love this venue, and I'm very, very pleased to be part of it. And
Thank you, Jack.
I think for a start, I'm gonna let it slide. Although I do have a final image that I want to show you, and I was hoping David would be here because I need to. I guess, do I switch my screen then? Share screen.
Yeah, go ahead and share again.
And the image I want to show you is Shoemaker Levy 9. And of course, David is the most famous amateur astronomer on this planet, I'm sure. Certainly he's the most famous Canadian astronomer. And when the Shoemakers and David discovered this, about 3 or 4 hours later, David gave me a phone call with this discovery, and they really didn't know what it was at this point. And so I took my telescope, and this was within 24 hours of discovery. And you can see the what they call a string of pearls. And but you see the haze around it, and again, cosmic dust that is associated with all of these objects. And
Jack, what did you think of this when you first saw it?
Oh, it just blew my socks off. I thought, holy cow, what a discovery. And
Now,
of
by
course,
this time, you knew it was a comet, correct?
well, you see the haze around it, especially down in here.
Yeah.
It sort of, gee, it's the funniest comet I've ever seen, because there seems to be individual parts to it. And it wasn't until, I guess, I think maybe 48 hours or 24 hours. I know that Brian Marsden was of course, he takes the reports, and he was at this huge convention at the time, and he had just been informed by his staff that this thing was going to go around the sun and hit Jupiter on the way back. And he couldn't believe his ears, and he didn't want to make an announcement in case he was wrong. And but they knew that within just a few hours after the discovery, once they got the orbit, of course, and traced it.
No,
out,
it's okay. It's good.
it went in right into Jupiter. At any rate, I'll wrap mine up. Thank you for having me on, and I'll be on many more times with lots of great slides for you.
That's great. Thank you so much, Jack. Thank you. I had never seen that particular image that you did before, but we were talking about it earlier, and you had just started doing color CCD work, and you really one of the only guys in the field doing color.
I took the first color picture ever taken with a CCD camera. That was a prototype of the ST4, and the Santa Barbara group sent to me. And then we were stopped in again on the way back, and they took out and showed me the secret project they had if I was sworn to secrecy. And
Yeah.
they had just a prototype of the ST8, and this was in sort of alpha. It had circuit boards in it that they had to clip in voltages in different spots of it. It was just a pile of wire and the camera stuck on it. And I said, send it to me, and I'll take pictures with my big scope. And so they did, out of the country.
Wow.
Headed to Canada, and I took the first color shots, and I was using the film off of chocolates that you get at Christmas time, and I got a red, green, and a blue.
Oh my gosh.
Machined up a little slide holder and took pictures and sent them on floppies to Richard Berry, who was the editor of Astronomy magazine. And they sat on his desk for about 4 or 5 hours, and it was driving him mental because there was no program available to put a color picture together on the computer. And
Wow.
so he wrote one and put the red, green, and the blue into it. And then he phones me and says, "You're not going to believe these images." And I think it was the Dumbbell Nebula that I had sent. And any rate, it was, and that ended up, I guess,
It ended up on the cover of CCD.
on the cover of
Astronomy.
CCD.
Yeah, I remember that.
Yeah,
It was mind blowing.
enough. But
Yeah.
we've had a lot of fun. Any rate, have a
Thank
good
you.
evening.
Thank you, Jack. That's awesome. And we look forward to having you back on when you're able to come on. So, and good
Super.
luck to the Newton
Oh.
Astro Club. I have posted a link in chat. So if you're interested in supporting this project, check out the website. And I think they have a Discord group that you can be a part of. And, and I'm sure there's a lot more to come with this project. So,
Jack, you've once again proven so many of my mentors that have done astronomy as a hobby or professionally for a long time. The old adage is, if it doesn't exist yet, build it yourself. And I think that's something that we who have come in, later kind of miss that whole part of, instead of buying it, which a lot of it's available, just getting some glue, some scissors, some tape, and some chewing gum and put it together and make it work. I really admire that spirit from, where, astronomy, I guess, comes from that to where it is now. So really appreciate the stories and the images.
Yeah, well, we'll tell you how many stars you can see in the daytime through my telescope.
I know of at least one that you could see.
I can split the double Epsilon Lyra in my telescope at noon.
That's impressive.
Yeah.
It's incredible. And that's a whole other story.
All right. Well, guys, we are going to bring on someone from the Goddard Space Flight Center, Dr. Caitlin Ahrens, who did a program called 7 Months of Science with us, where she brought on scientists from all over the country. And she, during these programs, she didn't speak a lot. For someone that knows so much, okay, and has so much to say, to kind of give her guests all that space was really cool. But I'm really pleased, Caitlin, that you agreed to come on tonight and to talk about space or dust bunnies in space. I think is what you. So perfect.
Okay. I gotta ask. I mean, usually when people ask me to give a talk, it's usually about Pluto and planets and bigger things. And so whenever you texted me last night saying, "Hey, you want to talk about dust?" and I'm just like, yes.
How much of a nerd am I, really? Where I can talk people into talking about dust, okay?
So let's make this the most exciting presentation about
dust program ever. Okay, it's all yours.
Oh my goodness. Well, okay, so a little bit of backstory too. So during my undergraduate years, I was an astrophysics/physics and geology major at West Virginia University. And when I started to learn about dust and that people actually studied dust in space, my first clue in that was like, why? just why? It's truly just dust bunnies in space. Okay. I'm quickly eating my words now, years later, because now I'm part of the dust team on Interstellar Probe, which I will happily talk about later. So now I'm part of my research is actually to learn about dust what all kinds of fun questions we still have about dust. So let's jump right to it, shall we? So it's so weird because I have my camera here, but my monitor is like right behind my camera. So you're gonna just kind of see me dart around a little bit here. So
all right.
That should do it. All right. So dust bunnies in space. Again, when Scott asked me to give this talk and he's like, what's your talk title? That was truly the first thing I texted, and I hit send and I'm like, am I gonna regret
I
this
love
title? Nah. We're all here to have fun. So
Yes, that's right.
if anything, dust bunnies in space sounds like the perfect movie title that you would have with Mystery Science Theater 3000. It really does. Oh my goodness. So the fascinating thing about dust, who studies dust? There's no just a dust person in astronomy. Instead, it's actually very, very interdisciplinary. So we dust bunny people. Some of us are geologists. We have chemists. We have astrobiologists. We have to talk to heliophysics people because we need to understand our sun. But we also have to figure out other exosolar systems as well. So we need to learn about other stellar systems. So we talk to those types of heliophysics people. Proto-solar disks and circumstellar disks and nebulae and everything like that. That goes with more of the astrophysics dust people. And then on a planetary scale, like I said, geology, chemistry, astrobiology, and also climatology as well. Unfortunately, a lot of climatologists are pretty much ignored, but they're very important to understand how dust would form in the planetary atmospheres or even some moons. So take like Titan, Saturn's largest moon. There's all sorts of dust that can rain down into the atmosphere. It's very, very thick and luscious atmosphere and cause all sorts of really fun atmospheric chaos, if you will. So very fun chemistry there. So what are we talking about when we say space dust bunnies? In this case, it's interstellar grains. This is mostly soot of space, but I don't really like saying soot, so this is why I'm saying dust bunnies. It's essentially material somehow just ejected by energy, ejected by stars, especially when stars are dying and then also being reborn, and so on and so forth. So the whole stellar cycle just has so much dust. Now, dust is typically very dense. They form in very dense and relatively cold environments, but they're released out into the wilds, into space. So you have the interstellar medium, which is essentially just the background of everything. But they can influence stellar winds. They can influence material. How does material clump together? All of that dust. Space is so dusty, and yet it only makes up about 1% of the mass of the interstellar medium. So really not that much, but they are still very, very important for stellar regions. I'll go to that here in a bit. So why exactly are they important? Well, if it wasn't for these magical dust bunnies of space, we wouldn't have stars and we wouldn't have planets. So, that's a pretty big responsibility for something that's just so tiny and essentially just dust. But think of it this way. You have a dust bunny ice grain, and these ice grains act almost like the La Brea tar pits of space. They attract molecules and stick everything together. So let's think of it this way. Hydrogen is the most basic molecule we have in the universe. And you try to get two of those suckers to stick together, no, it's not going to happen. However, interstellar grains, the surface of these grains are just sticky and cold enough that hydrogen atoms can stick to the surface and just happen to clump together. all with the help of a grain. So while all of these hydrogen atoms are now finally making H2, molecular hydrogen, all of that starts to build up and build up and build up. So as it's building up, again, these ice grains are supposed to be very cold and very dense. On the other side of the fence with this, you have just this hot, nasty, rapidly spinning gas all over the place. You need it to kind of settle down and get it cold. So dust comes into play here, cools that whole cloud down. And as the cloud starts de-spinning and cooling off, everything starts clumping together. Now you got stars to form better, you got planetary systems to form better. Everything is starting to cool down. And it's not just cooling down either. All that hot gas and everything is just bursting out what we call ionization. All this very hot energy. Again, dust grains could also act like shock absorbers. So they actually take in all that radiation. And instead it bounces right off of their little dust bunny bodies into infrared light, infrared energy. So they act as shock absorbers. They act as like the cool down pebbles of stellar clouds, and essentially helps with stellar formation. So very cool thing for just something so small. And there's different flavors of dust bunnies out in space too. So the typical ones that we would have in most solar system areas are the silicates. So you have silicon, magnesium, iron, anything with oxides. You could have carbon grains as well. So this is mostly graphite. There are icy type grains, which is mostly what I'm familiar with. So it's not just H2O either, haha. So the farther out you are in the outer solar system, now you're dealing with nitrogen ice and methane and ammonia. Ammonia makes a really fun ice grain as well. It's very sticky. And then you have something called PAHs. So PAHs, polycyclic aromatic hydrocarbons. So PAHs for short. So PAHs are the Lego bricks of dust bunnies. You would have truly just the most very basic Lego bricks that would be stuck together. And then you would have radiation to essentially break apart those Lego bricks and then reassembled, and then break apart and reassemble, break apart and reassemble. And they could form all these chains. Now, I don't mean chains like you're going to see them that big. No, we're still talking very, very small scale here. But PAHs really creates an interesting type of dust grain to study, because it tells us planetary people, I am a planetary geologist, but it tells us, okay, what type of radiation are we dealing with? PAHs are mostly associated with ice, so that can tell us what kind of radiation is happening now versus how much radiation happened millions to billions of years ago. PAHs are also found in the atmosphere of Titan as well, so that can really tell us how in the world does Titan form all these hydrocarbons, and how has it maintained that very thick atmosphere around Saturn. PAHs can also tell us a lot about our own sun as well. If we know how much radiation is going on through these chains all throughout the solar system, that can really give us a clue as to how much radiation our own sun is pushing out presently, and also millions and billions of years ago. So in that case, we look to the past, what are we doing in the future, and then in the present, and then how do we look to that in the future? The unfortunate part about all of this is that there really hasn't been that much done. There's been some, but yeah, we'll get to that. So like I said, the outer shell of these grains are very much like tar pits. They attract as much material on their surfaces as they can, and then they act like a shock absorber. But looking at the very interior part of it, I'm going to show you two different diagrams that I like that I found surfing Google earlier today. But it, very much like an Earth, right? You have the core and the mantle and a crust. So very, very micron scale. So you would have your inner metal or silicate as the core. Your mantle would be the buildup of either more metals or more ice, depends upon where you are in the solar system. And then your surface is going to have more of the clumping of whatever it attracts. It's either going to be more grains or certainly more organics. This is also another fun diagram that I like too, because then you get to see what happens to the outside of this poor silicate core in this case. So you have cosmic rays beating down upon it, and reaction products would be, again, breaking apart those Lego bricks and sticking them back together and break apart and stick back together. UV light, so all that solar radiation coming in, it's just going to keep blasting out infrared wavelengths back out. So it's all about location, location, location. Where in the world are these space dust bunnies? Are they under your bed? Are they on the stairs? Are they in the fireplace? It all depends upon where you're looking at. So circumplanetary or interplanetary, you're dealing with more local solar system. Interstellar means at least within the realm of our own sun, and then intergalactic, at least in between the different, well, as the name suggests, different galactic regions. So I'm just very briefly going to go through this though, but again, looking toward the heliophysics side of studying these dust grains, again, we want to see how is our sun irradiating. How's almost like the heated heartbeat of our own sun throughout the whole solar system. But then can we look to other exosolar systems as well? So we look at protoplanetary disks. How do other planets form? How do other stars form as well? Other star forming regions. Interplanetary, you would again go back into heliophysics, and planetary people have to chat, which is not easy to do. I can tell you that it is not an easy communication to do whatsoever, but it can be done sometimes. So looking at how planets are formed, look at how our own planets are formed. What are the different levels of like terrestrial planets versus gas planets, ice giant planets, and the Kuiper belt, and so on and so forth? You're going to have different types of grains in between and far out. And let's see here. I love these pictures though. So you have Trifid Nebula, M20, M20, so pretty, I love M20. And then this is M78. So I'm sure this has been mentioned previously to me though, but nebula are so beautiful. In this case, these are two excellent examples of what's called reflection nebulae. So reflection nebulae are essentially have almost like a bluish hue color to them. All this blue is essentially all that dust having that kind of a reflection, if you will, all that infrared radiation being bounced off of the grains, and it turns blue. So I'm not going to go through all these lines, but there are several detection methods, one of which was mentioned earlier by Jack, I believe it was meteorites. So go outside with a magnet. It's amazing how much micrometeorites can actually occur on a daily basis. So it can get really interesting. So meteorites, specifically larger, things of meteorites would be better to actually extract certain stellar grains out of them, though. But you know what? We have the technology to go smaller. NASA has done several different kinds of capture of like solar radiation type grains found in Antarctica and Greenland. The colder the better, better for preservation at least. My particular favorite detection method is something called aerogel. So aerogel, how we teasingly call it as the ghost jello. of material. It is very, very fun to play with. So I'll talk about aerogel here in a bit because it is very fun to play with. You could also have space telescopes. So the very specific one would be the Spitzer Space Telescope. This looks into the 3 to 180 micrometer wavelengths. So very long wavelengths, but you're wanting to get really deep infrared, thermal infrared wavelengths. You could also do polarimetry, but it's okay. But back to aerogel real quick. This stuff is so much fun. So it is. You can buy it for research purposes. That I may or may not have done so in the past. I have. So the careful thing about aerogel is that it's extremely strong. You cannot break it apart. You could actually heat it up and it won't melt. The only thing it is weak against is our own oil in our hands, in our fingers. So if you were to touch it, it will actually disintegrate within a couple hours. So you have to be very careful on how you handle it and wear gloves and everything. But we do have layers of aerogel in more current astronaut suits, actually, because they are heat resistant. So what you see on the right side of this PowerPoint slide, though, are just bricks of aerogel used for one of the Stardust missions. So Stardust was a fantastic mission from NASA to actually just go boom, right through a lot of dust and essentially just try to grab as much dust as it can. Now, the thing about dust, I believe I have in here. Yeah, so typically dust particle velocities are very, very fast, 10 to 40 kilometers per second. So that's actually there's pros and cons with this, right? So going that fast, you're gonna need aerogel as like that jello to shock absorb the grains and essentially eat the grains as much as possible to get as much material as you can. But at those velocities, yeah. The bad side about this, though, is that if you have those grains going so fast, there is a potential that those grains could actually shock themselves, or they can break apart or anything like that. Sorry, bad joke there. So past missions, we have all sorts of fun missions that have done a lot of dust work. So previously we've had Helios missions, Pioneer 10 and 11 also did a few, Galileo, Cassini did some fantastic dust analysis going around the Saturnian system. Voyager 1 and 2, there for a while, was using their Langmuir probes as a sort of sampling of cosmic dust. It didn't last long though, but it was a good try. Now the current use of dust detectors, most recently the New Horizons spacecraft and also Rosetta around Comet 67P, Churyumov-Gerasimenko. So these dust detectors are really quite interesting and they're constantly evolving. How can we be better about licking and sniffing and sampling all the dust bunnies of space? So what's the next step of cosmic grain detections? Well, we have the Interstellar Probe. So I highly encourage everyone to check out interstellarprobe.jhuapl.edu. Interstellar Probe is essentially going to be the next generation of a Voyager-like probe. It's going to hopefully launch, fingers crossed, in around 2036. For a launch date, it's going to have a Jupiter gravity assist, but it's going to just zip right through the solar system, but it's going to look at interplanetary dust. It's mostly a heliophysics type mission, so it's going to do a lot of radiation type experiments. It's going to do some fun Lyman alpha imaging as well, but I'm specifically helping a lot of the astrophysical dust folks on this mission. So it's going to be really interesting because, like I said, we have the pause, we have the silicates, we have the ices, we have the different kinds of grains. The issue, though, is that we don't really know what is the extent throughout the whole solar system. We only know maybe a little bit of dust here and a little bit of dust here. And oh, look, there's a comet. Oh, look, there's Saturn. That's about it. What is dust like in between the planets and then past Pluto? What is dust like? Is the radiation variable? Do you have pause type chemicals past Pluto? More than likely, yes, but what kinds and how structured are they? So that's essentially what's going to be some interesting questions to be coming about with Interstellar Probe. So that is my presentation. So I hope you guys enjoyed Cosmic Dust and Bunnies.
Awesome. It's awesome. You know, I think that the study of interstellar dust is a relatively new field. I mean, it seems like, I mean, when I got started in amateur astronomy, when we learned about interstellar dust, it was kind of like, well, you know, it's stuff that kind of gets in the way of the stuff that we want to see, right? It obscures like the center of our galaxy. We can't see the core very well because of all the interstellar dust. And we didn't really understand a lot of the dynamics of how like a galaxy breathes dust kind of, you know, to, you know, and its whole cycle of creating new stars and all of that. So it is, I think that, you know, these tiny little pieces of our cosmos are, you know, they do a really big job, you know, as far as you know, the creation of whole stellar nurseries and all of that. So what do you think is the most interesting part, or what do you think will be the most compelling part of the study of dust for yourself, Caitlin?
For myself, okay, good, because I'm not going to speak for the whole team.
Of all time.
Of all time. Oh my goodness. So for myself, I'm really interested to see just the Lego brick structure. How does that change in between planets and beyond? Because it's so fascinating that grains would like stick to each other, but their cores will be different. Their surfaces would be different. How well do they stick to each other? There's grains that we consider fluffy. So would they stick as well as those that look very angular and sharp and pointy kind of dust bunnies? But how does that change? Does it go from fluffy to angular to fluffy again? Is there a certain point in the solar system that it changes? We don't know. So you're right. I mean, it's interesting that we always just kind of been like, oh no, it's dusty. It's noise. It's dust out of the way. And now all of a sudden we're like, hey, we want to know dust now.
Yeah, that's right. Caitlin, thank you very much. And thanks for coming on Global Star Party again. It was awesome.
Thank you for having me.
Take care. Okay, so next up, we're going to Nathan Hellner-Mestelman. Nathan's presentations have been enlightening, humorous, and very energetic. Nathan, it's great to have you on our program again. And I'm not sure what you have in store for us today, but I look forward to it.
Oh, well, thank you so much for having me again. So today I was looking back on an article that I'd written about asteroids, and I figured this would be suiting for a global star party about cosmic dust. So this is actually it's a sport involving meteors, and not just any sport in particular. I call this cosmic dust, the extreme sport. So as it goes, some people suck at sports, and that kind of includes myself, because I like participating in sports, but I'm certainly not like exceptionally good at any of them. Luckily, there's always a shortcut for anything in life. And while shortcuts may not be very good ideas, as is often the case with these scenarios, if you haven't noticed already, I'm not in a desperate need to be better at sports, but I still wonder how I could improve. So the first technique to get better at sports is to train. That's admirable, but in the name of science, it's not really the most direct way to do it. There's a much more consistent technique, which is, of course, meteorites. And it's important to define this first because meteorites are meteors once they've reached the ground, and meteors are meteors when they're burning up, and meteoroids are meteors when they're still in space. And those three definitions have divided the space clubs of the world and cause 10% of all the arguments in astronomical societies. So with that aside, it is technically possible, albeit unlikely, for a meteorite to land a score in a ball sport, and that is what I'll be looking at today. So for a meteor to make it to the surface and become a meteorite, it only needs to be a few centimeters across, but it usually makes it to the surface in the form of tiny bits and pieces. So as Caitlin mentioned, these micrometeorites are really, really commonplace, but the bigger ones that make it to the surface are significantly less so. In order to really influence a game, meteors really should be around like maybe 10 centimeters across. That was my estimate. And most sports have balls bigger than that, but I figured that a 10 centimeter wide meteor would probably be more than enough to impact a game. No pun intended. Actually, you know what? That was a pun intended. So yeah, another thing we need to take into account is that the walls of stadiums and gyms could stop meteorites. So I'll have to assume this is taking place outside. So there isn't really good data on how many 10 centimeter wide asteroids there are in the solar system, because with the telescopes we have today, we couldn't possibly detect them all. But we can estimate, looking at the number of asteroids that are, say, other factors of 10 wide, like say 100 kilometers, 10 kilometers, 1 kilometer, 100 meters even. And with that trend continuing, I was able to estimate that in the entire solar system, there's probably around 312.5 quadrillion objects around 10 centimeters across. That includes the Kuiper belt and the asteroid belt and the Trojan asteroids around Jupiter and Saturn. But of course, objects in the Kuiper belt probably aren't going to impact life on Earth, except Pluto, which I think about every day. I wanted to figure out how many of these asteroids could actually impact the Earth. And of course, these are going to be near Earth asteroids, but even more than that, they're going to be asteroids that are directly impacting Earth. So I looked at the percentage of asteroids that are actually in a hazardous position. And then I was able to estimate that there's probably a 10 centimeter wide asteroid colliding with the Earth every 17 hours. And there's probably one less than 2 million kilometers away, in fact, that will soon impact the Earth. Now, once every 17 hours may sound like a lot, but as Neil deGrasse Tyson famously put it, 70% of the surface of Earth is water and over 99% is uninhabited. So you would expect nearly all impactors to hit either the ocean or desolate regions of Earth's surface. So why do moving meteors have such good aim? So this is the reason why you don't notice these 10 centimeter wide meteorites often. Statistically speaking, every square meter of the Earth's surface is being hit by, I'm gonna have to like take a deep breath for this, 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 10 centimeter wide meteorites per second. To say that a little faster, in metric units, that's 3.203 zeptometeorites. But I don't know if SI prefixes are working well here. So with those statistics, I decided to look at how long I'd need to play a sport for a meteor to actually impact the score. So firstly, I think I looked at tennis, which my sister has gotten pretty good at, but me significantly less so. So yeah, I can't hit a tennis ball very well, but a meteor might be able to help me here. So eventually, after playing tennis, if we were able to play indefinitely, like food and water compensated for, and maybe even assuming that the Earth doesn't get destroyed, eventually a meteor would come crashing through the opponent's racket, obviously winning me the game. That would take actually 161.7 trillion years, which isn't practical. The Earth would in all likelihood have been destroyed by the dying sun long before that. So I would have to assume that the solar system would be eternal, and given how many of the meteors would have actually already collided with other parts of the Earth, it would actually start using up the solar system's meteor supply. So I'd have to assume that it regenerates itself, which is slightly bending the laws of physics. It's also important to notice that I would actually only have to wait 49 trillion years, because by that point, it would be likely that the opponent directly would have been taken out by a meteor. So that would significantly decrease the time if you think about it that way. And also, I would, in about the same amount of time, also be taken out. So it's not really to my advantage either. So the most straightforward sport to incorporate meteors into is probably basketball. And case in point, meteors would fall through the basketball hoop every 6,032,000,000,000 years, which is, again, an awfully long basketball game. It's also just as likely that the other team would score a point via this method. So it's not really to my advantage either. The other problem here is that it's a lot more likely for meteors to fall on some other part of the stadium rather than directly in the hoop. So by the time a meteor actually fell into the basketball hoop, it would be statistically likely that everyone playing on both teams would have been taken out by a falling meteor. So that's probably not the best game to play either, if you're counting on meteors to do it for you. So the next sport I looked at was golf. And that's an interesting sport to use meteors for, because it's a hard target to aim for, but rolling to the target is an option. Unfortunately, most meteors aren't spherical, so rolling is kind of out of the question, but it still leaves the possibility of meteors directly falling into the hole. And that would take about 1.08 quadrillion years, which is much longer than all the other games we've discussed. But sooner or later, it would happen. But then it also raises another interesting thing, which is that given that it's a 10 centimeter wide meteor, and it's a 10 centimeter wide hole, that would mean it would have to have nearly perfect aim, meaning that every other 10 centimeter wide object on the field would have also been struck by that point. If you wanted your opponent to lose a point via a meteorite impact, you could also wait 7.07 quadrillion years and wait for their golf ball to be directly struck by a meteor. To be fair, these strategies aren't in the rule book, and I did check, they're not there. There's nothing about meteors. So imagining a more within the rules scenario, I decided to figure out how long I'd need to wait for a meteor to actually hit the golf ball at such an angle that the golf ball would be sent flying into the hole. So given that the average distance to the hole and the hole's diameter, you can calculate the apparent size of the hole in arc minutes and arc seconds, that stuff. So it turns out to be about 6 arc minutes, 3 arc seconds wide. And that corresponds to a part of the golf ball that you'd need to hit in order to send it toward the hole. And that area on the golf ball has a surface area of about 0.0041 square millimeters, which is really small. And for a meteor to hit that, it would take around 7 sextillion years, which is about 14 times as many years as there are grains of sand on Earth. So maybe it's not the best strategy. So yeah, so much for golf. So how about volleyball? Now, volleyball is probably my favorite sport, and I'd say I'm decent at it, but I'm not very good at what they call spiking the ball. Spiking is a move where somebody hits the ball directly over the net and downward so that nobody on the other team has a chance to hit it back up. Luckily, I am decent at hitting it over the net, and to spike it, I would just need a meteor to come down on top of it, hitting it directly down. I was surprised to find that that would only take 7.7 trillion years. Not fast or anything, but much shorter than the other strategies discussed. Unfortunately, most volleyballs can't withstand a meteorite impact, so the ball would be blown to pieces. And I haven't exactly read the rulebook for that, but I'm guessing it would count as a foul.
Yeah.
Yeah, I think so. So bowling is an interesting sport because it's literally the objective of the game to hit things. A bowling ball, like other balls, might actually be able to withstand a small meteorite impact because the Earth's atmosphere slows down rocks significantly. So it might only end up breaking pieces off, and that would take 1.3 trillion years. But having a bowling ball completely destroyed probably wouldn't count as a lost point either. So if you wanted to gain a point, you might think that you could stand in front of the bowling alley and just wait until a meteor comes along and knocks over all the pins for you. If you wanted to do that, and the meteor had to cover the full length of the alley, that's another thing to take into account. You could say that a meteor could just come directly down on the pins, That's not really bowling though. So if you say it has to travel along the alley like it was a bowling ball, you'd need to wait 990 trillion years. It might actually take less time than that, because it's assuming that the meteor acts like a bowling ball. And when you're using a bowling ball, you need to be very specific about the trajectory and stuff, because if you don't hit it right, you won't get a strike. But for something as destructive as a meteor, you could probably hit the pins anywhere and still get a strike. That would reduce the time to 79 trillion years, which is definitely sounding more convenient, don't you think?
Depends on how well those kick plates are in the walls. If it bounces
Yeah.
pins around,
Right.
you have a better chance coming from a bowler. So yeah, that might work.
Perhaps.
It would be before I could get a strike. Sometimes it takes me that long to get 9. Carry on.
So yeah, at this point, I kind of started to ask myself, what the heck am I even doing? I mean, if I used this strategy to try to beat someone at bowling, they would have scored like trillions of points by the time I even got one. So in looking back on the article that I wrote about this, if I might have written something a little bit wrong here. I was probably wrong about the starting line, so I might have to go back and change that. So I feel the most fitting sport for this scenario is dodgeball. The objective is to hit people out with balls, and meteors could probably do that too. Then again, I couldn't find anything about meteors in the rule book, but if my guesses serve me right, that would most likely probably be okay. Like I mentioned, it would take 49 trillion years for any given person to be taken out by a meteor. But in a game of dodgeball, given that people are so good at dodging, they might manage to significantly prolong the time it takes to be hit by a meteor. And if the game extends long enough, I found that statistically some very interesting things happen. So if you threw a ball directly at your opponent, you should expect to miss a shot after 219 trillion years, due to the fact that a meteor would collide directly with your ball while it was in the air, knocking it off course. And if you threw a ball at an opponent and it completely missed, then after 129 quadrillion years of playing, it becomes statistically likely that you would still get someone out due to the fact that a meteor would knock the ball off course and directly into an opponent. If you were to play dodgeball against a team for 549 decillion years, which in scientific notation is 5.47 times 10 to the 35 years, you might get extremely lucky. I mean, actually, lucky is a weird word to use because like you'd be pretty unlucky in this situation. But it would be statistically likely after 547 decillion years that while an opponent was throwing a ball directly at you, 2 meteors would simultaneously fall from the sky, one of them taking out the opponent for you and the other one taking out the opponent's ball. And lastly, just to finish things off, if you ever had the misfortune of being forced to play a dodgeball game alone against 10 opponents, all you would need to do is avoid being hit for 3 million Google years, which is 3 times 10 to the power of 206 years. And by that point, it would be statistically likely for 10 separate meteors to simultaneously hit each of the 10 opponents out. All right. The moral of the story, I don't know if there's anything to be learned here, but maybe it's just to say, practice hard to get good at something and don't rely on meteors to do it for you. So thank you so much.
It was amazing, Nathan.
So Caitlin, what did you think?
Oh, yes. I too am not good at sports either, so this makes me feel better about myself, if anything. This is fantastic. I loved your presentation.
Thank you so much.
It's a great presentation. Now, I did play sports. I interjected with the bowling because I still do that. I'm not telling you how many bowling balls I have, but it's a lot more than the meteors that I expect to hit in the next 5 hours. But yeah, I love the analogies. And as far as being good at sports, you don't have to be, because we all get old and creaky at some point and then can't do the things we used to be able to do when we were younger. So while you're young yet, just enjoy it. I'm pretty sure you can run faster than I can. And excellent presentation on the time scale. Your math really really shows the type
Yeah.
of probabilities and time scales
Threw out some
for
numbers I've never
certain
even heard
things.
before. So
Yeah, that can happen. So, we worry about the meteor coming right this moment, but the reality is the probability of it is not as good as the movies may think it is. I really like that quote you had from Neil deGrasse Tyson. How do these meteors have such great aim? So yeah, excellent presentation all around. And you're more than welcome to come bowl with me sometime when you're in Michigan.
Well, thank you. I'll try not
You
to
all
bring any
and
meteors.
that I extend that invitation to everybody. If you want to come bowl, we'll have a great time.
You need to put a timer, Adrian, because Nathan will wait.
All right, I'll click the timer right now. I'll see you in 3. What was that number, Nathan? 3.
I don't know. You can just say any number with at least 20 zeros after it. It's
Yeah.
totally fine.
There we go. We'll wait. Hopefully, I'll be in Argentina before that happens.
yeah, I'm sure you
For
will.
sure.
All right. We are going to take a 10-minute break, and we'll be right back with Conal Richards. So stay tuned and go get a coffee or a sandwich, or stretch your legs. We'll be right back.
So Nathan, some of the numbers that you predicted, there are sports fans of my college team that thought it would be that long before they would see our football team make a college football playoff, let alone a championship. And we're still waiting that long for the championship, but they did make the playoff. So they came in well under the 3 10 to the 20th time years that we thought it would take. So stranger things can happen.
Hey, Nathan, quick question. I heard you mention Pluto. Do you like Pluto?
Oh yeah. I went on this survey. We were doing like a class survey, and I was heartbroken to find out that like I was the only one in the class that actually thought about Pluto, and it was just heartbreaking. Like one of the questions I asked was, how do you feel about Pluto's status as a dwarf planet? And like 2 people said undecided, and the rest of them were just like, don't care. So we need to promote this. And I think it's perfect to be saying it on a global star party. We need to start a movement to make Pluto an honorary planet.
Oh my goodness, yes. 100%. No. You need to get my contact info from Scott. We'll chat Pluto.
Okay, cool. I think whichever organization we create, it'll be a plutocracy.
Oh, the puns are strong with you, young Padawan. Oh my goodness. But yeah, we definitely need to chat Pluto.
Yes.
Nathan, I have to ask you, have you ever read a book called What If?
Oh yeah, I have all of Randall Munro's books.
Really?
Yeah, that was mainly my inspiration for thinking of these just like wacky hypothetical scenarios. Yeah, I have a very large collection of these just weird scenarios, and I think that was what inspired me. So, yeah.
That's awesome. I really do love that book. I thought I saw a little bit of his inspiration in some of your jokes, so I enjoyed that a lot.
those of you that are chatting, Chris, the silence is deafening, and Pluto's definitely a planet. I'm in agreement with you on both. We all went to get coffee and take care of other things. I've got mine here. You can't see it because I have a virtual screen. And I don't know if you can even see, you can hear me talking, but you can't see me anyways because the chat is visible. I think everyone else stepped out.
I put up a in chat the page for visual comets in the future. This is and there's quite a few of them that are listed on here. It looks like maybe, I don't know, maybe 100 are listed. This is by Saiichi Yoshida and his comet page. But it's an incredible resource, and I think you'll enjoy it. I don't know, maybe 100 are listed. This is by Saiichi Yoshida and his comet page. But it's an incredible resource, and I think you'll enjoy it. I don't know, maybe 100 are listed.
I think I heard you twice, Scott, but we'll have to check that.
I think I heard myself twice as well. I don't know why.
Well, it's not happening now, so we're all good. Yeah, when you mentioned the topic being dust in the Milky Way, it changed the directory of my talk. I think the word is directory. It's more direction of what I'm going to present much later on down the line. So I actually did a little research for it and found some interesting things about the center of the galaxy that I'll be sharing. Not as many pictures, but still some interesting things that I noted. The hint is I found a Spitzer Space Telescope image of the center of our galaxy. So I'm going to work that in somehow. So we'll see how it goes.
Excellent.
To Chris Larson, who says Pluto is a planet. Congratulations, Caitlin. We've gained our first revolutionary.
Yeah, I think we already had with Dr. Alan Stern spars with Dr. Neil deGrasse Tyson, and many others who cite the properties of Pluto and the fact that it may, if it were closer to Earth, it might grow a tail. But I like the argument that if you're close enough to the sun, you're probably going to grow a tail regardless, just because the material on you is going to begin melting off, and if you're moving, a tail will form regardless. So that's, there's other characteristics of Pluto that might resemble the makeup of comets more than the makeup of our gas giants and our rocky planets. But the debate rages on.
Well, hello, everyone. We're back after our 10-minute break here. We were talking a little bit about Pluto and someone mentioning I guess it might have been Neil deGrasse Tyson that if Pluto is closer to the sun, it might develop a tail. I'll argue that Mars has a tail. It's got dust that is being spread around the solar system, and they have determined that it is the probable cause of the zodiacal light that we see. So anyhow, it's and perhaps maybe even the Earth itself outgasses some material out in space as it zooms around the sun. Who knows?
We definitely outgas a lot of materials to space as human beings, so that should count. And as of zodiacal light, you just gave me an idea of other things to present. So I'm gonna go look for those images.
Okay. All right.
So
Yes.
carry on.
This
cool.
theory about things being close to the sun developing tails, are we then to believe that cats and dogs have developed tails because their surface material is melting off from the heat of the sun?
Yes.
That's the reason.
Fascinating.
That and rabbits too. Most animals.
All right. Well, Conal, I'm going to give the spotlight to you. Thanks for coming on to Global Star Party yet again. You're becoming a regular, so it's really cool. And what is your program, your presentation tonight?
Well, tonight, the theme being cosmic dust and dust bunnies and everything that comes along with that, I thought I'd go back and share some of my photography. I have a couple of old shots from the Milky Way from past summers, mostly looking over towards Sagittarius and also through Cygnus. There's some of the brightest regions with a lot of definition and contrast in dust and nebulae and things that we can observe. So I'll start by sharing my screen here. Of course, let me know if you can see everything all right. Should see a folder in front of you?
Yes.
Okay. So we'll pull this up here. This was actually taken right from my backyard. This was a shot right around Cygnus, taken from a summer or two ago. And if we look up above these trees, right here is Deneb and Cygnus. And over here, above and below, are the wings of the swan. And it's a little hard to follow through because there are so many stars in this image. But if we trace back, I think this should be Alberio right here. We have Colander 399, the coat hanger right there. So there's so much to see right in this wide field image of the Milky Way. But most apparent, we see this star cloud here, this kind of white patch against the darker sky where we're looking out of the plane of the Milky Way. We see another white patch, and then it gets a little darker as we're moving away from the Milky Way. But right through here is a part of the Milky Way that we call the Great Rift. And Dr. Ahrens was talking a lot about some of the particles that we find here, some silicates, hydrocarbons, all sorts of clumps of carbon and dust that even get a little bit icy, and they block out some of the starlight. So of course, we're looking way out in the Milky Way. The Milky Way is about 100,000 light years in diameter. So this could be tens of thousands of light years of material that we're looking through. And with so much of that space and so much interstellar dust filling that, some of the starlight might be kind of dimmed or hidden behind even with so much dust in there. And if we look at other galaxies in our telescopes, M51 is a great example. You can see dust lanes in there. The Sombrero galaxy, where we're seeing it edge on, you see light above and below and this huge dust lane right in the middle. And this is kind of what we're looking at, but from the inside out in our own Milky Way. So it's a feature I find really interesting. You can see it from many dark sky sites when you're looking up, and it makes a great subject for some wide field photography during the summer. And you could even do a more artistic take on this. This was a much longer exposure, about 15 or 16 minutes looking south, probably the same night I imaged that region of Cygnus. So we're looking south here and you can see the star trails. I think they're quite beautiful along with the trees. But if you look more carefully, you can see a portion of the Milky Way here. And this should be right around Sagittarius. So looking kind of towards the center of the Milky Way, you see a little bit of that white cloud here and a little bit of a dimmer white cloud over here. And it's blurred by the longer exposure in the star trail. And I was curious to see what this looked like. But once again, you see this rift of dark material in the middle. And it reminds me of a lot of the old folklore and mythology that talks about the Milky Way as a river. I think when you blur it and look at it as a long exposure, this kind of brings those stories into perspective. And I thought that was a really fun way to look at the Milky Way. Now, once again, this was taken from a local state park, a clearer image of Sagittarius. We see the teapot asterism down here. This would have been the summer of 2020, I believe. Over here is Jupiter. Saturn wasn't far behind. But then coming out of the spout of the teapot, if you will, is that darker region of the Milky Way we saw in that longer exposure, the star trail, and the Milky Way growing up and eventually reaching Cygnus way up here. But down here, we see different types of dust, not just the carbon particles covered in ice that are kind of blocking out the starlight. We see a reflection nebula here in the Lagoon Nebula. You can see the little star clusters just captured as pinpoints in there and a little bit of a cloud around that, kind of standing out from the background of the rest of the Milky Way. So that's a very bright and beautiful nebula. It looks great in binoculars. And of course, it's a great subject for some deep sky photography if you're looking at things with a wide field. And if we go up here a little bit, this is an object in Messier's catalog, M24. It's the Sagittarius star cloud. And if you look at some of the papers and the research behind this object, you find it's actually not really an object at all. If we see this huge clump of dust blocking out the center of the Milky Way, we found that eventually it clears up and you're looking through almost a tunnel of dust to another part of the Milky Way and seeing this huge cloud of stars in another part of our galaxy. So that's a really fun sense of perspective to bring into your observations or your photography. You can see the dust and light, which is a little bit closer by, even though it's kind of amorphous and dimmed down a little bit. But then when you look through this hole in the dust here, you see the Sagittarius star cloud and a couple of little stars in there that are in the foreground. And even farther up, I was just looking at this image earlier, you can see up here is M16, the Eagle Nebula, and M17, the Swan Nebula. And you can't see much detail in them, but like the lagoon, there they are as little drops of light kind of bursting out from that dark rift in the Milky Way. Now I'll take us back again to that image of the Milky Way I was looking at first, that Cygnus region. And I had one image that I designed to look a little more artistic and pretty. But with this image, I wanted to see, just to find what I could, if I really enhance the contrast on this region of Cygnus, and what could I find in there? Would it bring out these dark lanes a little bit more? And you can see the North America Nebula is hanging out right there, another patch of light. And then this great rift is passing through once again. But one of the reasons I wanted to look at this image is a zoomed in portion of it here. And it really doesn't look like much, of course, but if you look carefully, there is an E asterism. This is, of course, Barnard's E. So you have Barnard 142 down here and 143 up here.
Mm-hmm.
You see that there?
Mm-hmm.
And that is much like the Great Rift going through Cygnus. You see these dark nebulae here. There are these huge clumps of carbon coated in ice and blocking out the starlight that would be behind it. And sometimes they make some fun shapes and they make for some fun catalog objects. And as exposed and pixelated as this is, I was curious to see what I could find with my camera. And it was really interesting to find that E-shaped asterism. Now, as for some other instances of dust in our solar system, this is Comet Neowise, an image I've shown a couple of times on Global Star Party during its evening apparition after it came around the sun. There's the nucleus of the comet there. Of course, it's screaming out of our solar system at a great speed. But there is a really beautiful instance of dust in our solar system. The comet has begun to outgas as it got closer to the sun. And you can see the intensity is growing very close near the nucleus and a little bit farther away as that tail fans out in these very fine wisps of dust. Now, that's all I have for the dust tonight, but I do have a couple of images I'd like to share. Of course, I was thrilled since I got on break from Penn State. Our skies cleared up a little bit and I was out and I thought I'd take my chances with imaging the moon and Saturn and Jupiter up here. These are only the raw images so far. I got these about 2 hours ago, but it was fun to get the camera back out there and see what I could find. I think I had some moisture on my lens because these were only 5 to 10 second exposures and the moon seemed blurred a little bit. I couldn't quite get it to focus. So I tried to experiment.
Very nice.
I do too. Sometimes you can make the colors really pop, even with the settings on the camera. And that's really great in post-processing. But this image came out a little clearer. You see Saturn over here and of course the moon. But the moon I thought was really special because if you look carefully, you can see the Sea of Tranquility over here, the Sea of Storms over here, Oceanus Procellarum, and then that hook of the waxing crescent there, kind of overexposed against this earth shine. But you can see some of the seas on the moon, which I thought was really beautiful. I'd never really been able to image that before. So I think our moon is only 2 days old right now. That was a really fun target to check out. I got closer on the moon once again here, and you can see the seas so much better, a little more pronounced. Sea of Tranquility over here and moving over. I think this is the eastern limb of the moon right here. I could have that wrong. But nonetheless, you can see some of the seas and some of the brighter craters and ray systems through the earth shine. And then, of course, that well-known crescent shape in the blue of twilight through the trees. So I think, you know, cosmic dust always makes for some wonderful images. I really enjoy looking at the Milky Way and comets and all sorts of things that have very fine particles, but great quantities of them. And they make for some great images and fun targets to observe. And then, as always, I like to look around the solar system's neighborhood and see what the moon and planets are up to. They always make for some fun images. So thank you very much for having me on. I'm always happy to share some photography.
Conal, thank you so much. It's great to have you on. I know that you give presentations to other groups and clubs and stuff like that. Where else have you given talks so far?
Well, I started off actually, after I got to know Chuck Allen through the Astronomical League, I spoke on one of the League Live events, and that was done to promote some of what I was doing in my astronomy club. I'd spoken a lot at my astronomy club at my high school. I founded that junior year, and senior year, once we were able to get back in classes and we really had the club rolling, I gave some talks there about naked eye astronomy and binoculars a little bit. And we also had some small crafts and exercises to look at maybe the scale of the solar system. We did another one. We took some cloth and some different sized marbles with different masses to look at how gravity can distort space-time. So you have black holes, then planets and stars on different scales. So on this platform, I really enjoy sharing photography or sometimes some of my favorite targets for a given topic. Sure. But then hands-on demonstrations are fun to do as well.
Have you given any planetarium programs, like in a planetarium setting?
No, I have not. I'd like to do that.
Very good at it. So the way you describe the sky and you take people through the constellations and stuff, you do an excellent job. And I think that I think you could be a great presenter in that, you know, in that arena as well. So anyways, just keep up the good work, and hope to see you back on another Global Star Party.
I appreciate that. Hope to see you again soon.
Yes. Okay, so up next is Khoa Tran from the Royal Astronomical Society of Canada, the Montreal Center. He and Karim Jaffer were supposed to be on together, but Karim had some family matters he had to attend to, and so we're glad to have Khoa on. Am I pronouncing that right?
Pretty close.
Is it pretty close?
It is really
not
close.
Exactly right.
Hey. As I've gotten older, you know, you learn to give positive.
You get more.
Yeah.
He shows sympathy towards those that can't actually really speak very well. So.
That's all right. And it's one syllable. Khoa.
Khoa. Okay.
Khoa. Yeah.
Khoa.
So
Khoa. Okay.
The
all right.
International Phonetic Alphabet. It would be KWA.
Okay.
Or Italian for here.
Perfect. And that's a beautiful collection of guitars behind you.
Thank you very much. Yeah.
Do you play often, or?
As much as I can now, you know, working full time, 50 minutes away from curfew with a toddler whom I hope isn't going to start screaming during the middle of my presentation. But no, I've that's about a quarter of what I've got.
Oh, wow.
Well, but no, it's good.
I'll have to get you on a Global Star Party to hear some of your music sometime. That would be great. Okay.
It'd be a pleasure. All right. Thank you very much. So thank you, Scott. Like I said, my name is Khoa, and I've been a member of the Royal Astronomical Society Montreal Center for the past few years now. I do a little bit of everything. I like to look at pretty things in the night sky, and I try to take pictures of them every so often. Hello from Montreal. We are about 39 minutes away from yet another curfew, and the temperature has risen quite a bit in the last over the last year. So we're at 270 degrees Kelvin. That's balmy, even. So I was supposed to give this talk back in late November for the Looking Back edition of the GSB, but I had to bow out because, you know, when you have a toddler in daycare, the first year, apparently you catch everything. So I had no voice. I could barely, read a bedtime story, let alone, give a presentation. So we'll take a trip back. We'll look back at the looking back edition of the GSP from November. I'm very excited to look back over a few decades at the first book that ever got me interested in space. And there's probably some cosmic dust in there, I'm sure. There is absolutely terrestrial dust in it because it's like 40 years old, this book. So I'm going to, for the interest of bandwidth, turn my camera off, share my content. Et voila.
Here we go.
There we go. And I'm going to open that. All right. So I can't really pin it down, but sometime around 1986, when I was a little boy of 6 or 7, a friend brought along this big, heavy picture book to class to share with everyone. I probably only had a couple of hours over a few days with it, but looking back, it was almost certainly what got me interested in space and astronomy. Of course, that's the National Geographic Picture Atlas of Our Universe by Roy Gallant. It's what got me interested in space and astronomy beyond imported Japanese animation of the time, like Robotech, Astro Boy, and Voltron, of course. So after many years of fruitless searching, I recently was able to find a copy of this myself. And so let's have a look back at a simpler time when there were surprisingly so few real photos of space that a picture book atlas of the universe was largely filled instead with awesome sci-fi illustrations like what you see on the cover. And as we look through it, it really shows how far we've come along in the past 4 decades or so now in terms of astroimaging, especially at the amateur level. So this is a glossy hardcover book with those aforementioned sci-fi illustrations and also some cheesy extruded text effects that from that time period. Published in 1980. It's about 11 inches by 11 inches hardcover filled with 278 glossy pages, not entirely unlike the feel and texture of a contemporary issue of Nat Geo. And to me, at the time, little 6-year-old me, it must have weighed something like 3/16 of a metric ton. It was heavy. And again, it was published in 1980. And by the time I got my hands on it later in that decade, in 86, 87, it was already quite outdated. So you have a quick look at the table of contents. And what's interesting is you have a handful of pages dedicated to the history and prehistory of astronomy. And while this is supposed to be a picture book or an atlas of our whole wide universe, the bulk of it is actually devoted to the solar system. So here's the prehistory and history section of in the book, from sun gods to gamma rays. I kind of like that chapter heading. Here's a nice little illustration of the zodiac. And a lot of the photos in the book, understandably, because there were so few pictures of space back then compared to today, are actually pictures of things on Earth, including this breathtaking one of the observatory Pic du Midi in the French Pyrenees. And as an aside, before drones, this would have been a really expensive helicopter shot, but it's gorgeous. I love it. Yeah. And here's a nice illustrated family portrait of the solar system. Pluto's not there, but that's just because this page spread is so wide that it doesn't fit on my flatbed scanner. I did not leave Pluto off on purpose. I swear I leave politics out of this. And you also see the middle school library stamp from, I can't read the stamp from here, but where it was, but it was from a middle school library. But what I remember most as a little kid were actually the portrait illustrations of the Greco-Roman gods and goddesses for whom the planets are named. These were done by an artist named Michael Whalen, who would go on to become probably the most decorated illustrator in sci-fi. He's probably got a handful of Hugo Awards by this point. So Mercury was my favorite planet as a kid because of this very picture. I mean, look at him. He's got winged shoes and a badass staff. I mean, it's like for the longest time, you asked me, well, favorite planet? Mercury, fastest thing around. And then there's Venus, and according to myth and legend, you know, she had doves pull her chariot. I would hope bigger doves than this one. And speaking of Venus, here's one of the very few images we have of the planet, the surface of the planet Venus. It came from one of the ill-fated Venera landers from the 1970s, which, you know, and according to the text here, it survived for nearly 2 entire hours before it got wrecked by the surface conditions. And more planetary surface pictures from the mid-70s. We have before Perseverance, Curiosity, and the rover predecessors, we had the Viking landers on Mars. And going back to Pluto, because he was considered a planet back then, of course, he gets his own section, and the Earth's moon gets her own section too. I really like that illustration. So as we go through this book, and most of it is really about the planets in the solar system, and they knew their target audience well, because, you know, schoolboys and girls, you know, elementary school kids, that's all we knew about, and that's what we found so fascinating. But what really strikes me looking through this book as an adult and as an avid astro imager is just how far we've come in terms of astrophotography, especially by amateurs. So I still shoot a lot of film artistically, but in astrophotography, I think it's not so much, you know, the digital cameras themselves, but, you know, all the imaging processing technology and techniques that came with them. Things like long exposure image stacking for deep sky objects, and, you know, and what we call lucky imaging that we do with video frames on solar system objects like the planets. So in this case, Voyager's flyby wouldn't be for another year before this book was published. So this ground-based telescope image of Saturn, Go Arizona, was one of the best we had up until that point. And it combined 16 separate, you know, film frames or image plates, whatever they would be using at that time. And these days, I can get an image like this with a 4-inch Explorer first light refractor, taking about a minute's worth of HD video, and then choosing the few hundred best frames to catch, you know, during those rare moments of best seeing through atmospheric turbulence. It is all about, you know, luck. And if you take enough frames, you know, you're going to luck into it at some point. And of course, you know, I know serious planetary imagers blow me away because they've got telescopes that are like planetary cannons. And what I've got is more like, you know, an antique musket. And speaking of antique muskets, inset, ignore the big image for now, but the little one, I took that with an actual antique musket. It was a 1960s Criterion Dynoscope 4-inch reflector, again using HD video and lucky imaging, and that's, you know, 2 Galilean moon transits flanking the Great Red Spot. And, you know, but obviously there's no way we beat Voyager's close-up image. That's just gorgeous. I look at it, and it's even better in the book with the amazing color depth that you can't really get from a scan of the image. And back when this book was published, we had this grainy picture of Neptune, which was groundbreaking in 1979. Also Go Arizona. In 1979, it was the first photo that showed detail on the planetary disk. And Voyager 2 wouldn't fly by Neptune until 1989. I still remember that time because I was about 10 years old. And those brand new science books with that brand new book, like that brand new book smell, you know, containing awesome photos inside. It was amazing. And then here's a 1978 photo of Pluto. And this is the photo that led to the discovery of its moon Charon. And I mean, you look at this photo, and then, you know, you only have to cast your memory back about 5 or 6 or 7 years now, actually, to what New Horizons sent back in 2015. And just think of how far we've come in that time. Now for deep sky photos, here's an image of the Andromeda Galaxy captured by the famous Palomar Observatory. And you could look at this image for days because there's just so much stuff in it. And you think this is a film plate, or like a chemical plate that's capturing this. So it's got to be, not what we do today with hundreds and hundreds of frames, stacked over, however many hours that we're taking these days. We do in amateur work. But this is what I was able to do in 4 hours and 21 minutes worth of exposure time from my balcony in the middle of a city, a metro area of over 4 million people here in Montreal. So I call it, hashtag deep sky from downtown. So I don't doubt, let's be honest, let's be real. Like the Palomar image definitely has more detail. And especially if you had access to the original plates, it would have way more detail than what I can resolve with a little 50 millimeter refractor. But it's one of those things where if you had told me even a few years ago that I could pull off this sort of image from my balcony in downtown Montreal, I wouldn't have believed it.
Yeah,
and I don't imagine. Yeah. And imagine an amateur back in 1980. Would you have been able to dream of something like this?
Nope.
And similarly, here are a couple images of the Pleiades star cluster and of the Horsehead Nebula in Orion. And I still remember this, looking at this very image. And that was one of the memories I had that kept taking me back as an adult to trying to find this book, was just that this image of what looked like a chess piece, like a knight burned into my brain, is just that impactful to me. And then so here's what I've been able to do with just over an hour in a park about an hour's drive outside of Montreal, and the Flame and Horsehead Nebula, this time from my rooftop deck at my condo, and it's just one of those things where it comes full circle. It's like, little kid looks at a picture of a chess piece, and then 30 some odd years later, it's like, hey, look at this. I actually did that. Yeah. Right. So, and I mean, this stuff, this is a what you might call a dual narrowband image. There's a lot of stuff missing. I could go deeper. There's a lot more you can add to it. But it's one of those things where it's like, again, 10 years ago, you tell me, oh yeah, you're going to take a picture of the Flame Nebula and the Horsehead, and you don't have to go out to a dark sky site to do it. You can do it from your balcony at home, because you can do it after you put your kid down, after story time, and there's really something special to that, I think.
Yes.
Yeah, and so the takeaways is that I think we're truly spoiled today with the breadth and the accessibility of the options that are available to us in astrophotography. And I look forward, however much time I've got left in this world, what the next few decades are going to bring in terms of advancement. And so this concludes my little look back to where it all started for me. We moved around a lot when I was a little kid. And so I was never able to find that book again at school libraries or at public libraries, probably because it was out of print and hopelessly outdated by then. But thanks to some of the computational leaps forward that have enabled modern astroimaging, I was able to find this book again. Coming to the rescue were technological advancements in the name of Google searches and eBay auctions. So that's it. That's it for me. I hope you enjoyed this little look back with me, and thank you very much.
Thank you, Khoa. Looking back as you have, really took me back as well, because I started off as a film astrophotographer back in the late 80s, early 90s, and you look at that Horsehead Flame Nebula shot, and we would have died to have been able to capture that, on film, and it would have been like climbing Mount Everest or something to get something of that detail, and to know that you shot that in borderline skies, and it's incredible. So I am with you on understanding how far we've come in just, these short few decades. So
yeah, and I started off with like a barn door tracker and slide film, and taking and scanning that slide film and then trying to stack the frames. This is like astronomy on easy mode now.
That's true. But when it shows you also, if you apply digital imaging as hard as we did film, how much further you could really go, so. Khoa, thank you very much. We'll see you next time you're able to come. Thank you very much.
Absolutely. Thank you.
That's a really cool guitar behind you.
I know. I was thinking the same thing.
So. Is that a guitar? The reddish one.
The red one in the middle, that's a 1960s it's a Mastro Macaferri guitar. It's made entirely out of Dow Styron plastic. And so this is more like a toy, but Mario Macaferri was a New York guitar maker, and he set out to prove that he could make serious instruments out of plastic. He failed miserably, but but now his instruments are worth money because people kind of got over that snobism.
They were just made out of plastic. Yeah. Right. Could he play them well?
He probably could. I think he was a classically trained guitarist. And
right. Interesting. Okay. All right. So we are going to go to, we're going to have Hammertime with Nico. Nico, it's great to have you back on Global Star Party, and looking forward to your presentation.
Thank you, Scott. Hi, everyone. I hope you all had a great New Year night. Yes, a few nights off for me, but by different ways. But I am really happy to be here with you. Okay, let me share my screen. Here. Okay, are you seeing it?
Yes.
Okay, well, tonight we are talking about the comic dust, and we had amazing presentations. I was fascinated with the Caitlin presentation about talking of the components of the cosmic dust. It was amazing. And I would like to talk about with what can we really see from here, from Earth. So the first thing I think about was the zodiacal light that we can see on the sunset or sunrise. And I don't know if you get the chance to see that. I am trying several times to be in the right place in the field, but I had no luck yet. This is an animation I took from internet, but the zodiacal light is really cosmic dust that we are watching that is in our solar system. It's dust from comets, from asteroids, from dust on the Kuiper belt, and almost interstellar dust that is just passing through our solar system. And in that 2 moments, in the sunset and in the sunrise, it's maybe less than an hour than if you are in a really nice sky and it's a clear night. You can watch this light coming from the horizon. And I really hope I could watch this in a field sometime. So as always, I want to show about hand tracing this kind of objects and things that we talk, and talking about dust. I thought in the nebulas that I could get with my Dobson, my hand tracking Dobson, because I don't have any motors. And I was looking for some nebulas that actually has a lot of dust in there. Like this is the K-hole nebula in Carina Nebula, and I really love to chase these dark spots, dark nebulas among the nebulas. Here we have another example. This is the in the Eagle Nebula, the pillars of creation. This, I think, is one of the most beautiful image I can get here from my home. I never thought that I could get this image with my Dobson, because I was making like a machine gun, a lot of exposures of 0.2 seconds, and when I stuck. And I saw that pillars, I was mind blowing. Yes.
How many seconds have, or fraction of seconds have your picture each take, Nicolas?
This take is each image, each frame is 0.2 seconds of exposure.
You listen, Molly.
That's crazy.
No, this guy is. Yes. I think something that. This guy is amazing. We found. Yes. Where I grew in my childhood, he lived actually maybe no more than 20 blocks. I don't know if it's the water of the neighborhood or something, but this is magic. But not for me, of course.
It's only perseverance. Yes, I think for this picture, I took it with my Khoa monochromatic camera. So I was switching filters and putting the camera again and refocus and keep shooting. I was maybe 1 hour shooting and 500 pictures of each channel to get this image.
So that's 0.2 seconds unguided, right?
Yes, unguided.
No, words.
It's worse than that. It's 0.2 seconds hand tracked. This is not a tracking mount.
Yeah, let's underline that.
Yes.
It's a very good point.
Yes.
With the
skipped right over the fact that it's hand tracked.
Yeah, and you need to track in the two moves, because you need to move the altitude and the azimuth move. No, it's really contracturing.
No, I need to go to Banfield, your neighborhood, with my CWO 224. It's okay for that?
Yeah, sure.
It's not monochromatic, but okay.
No,
okay. I'll go with a small sensor. It's okay.
Yes, this is what was taken with the HY5. It's like a really small sensor. It's a guided camera.
Yeah, my idea is teach to the kids using this small telescope, not with this mount, if not with the normal mount that is azimuth mount, to make something like this. Because with the cell phone, or much better with a camera, with a cheap camera for planetarium or guiding. Yeah, yes. I need to learn from you, really. Yeah.
Yes, we will.
I pay you, no problem.
No, it's for teaching. I love that.
I can pay you with eyepiece.
Yeah.
Jeff Weiss on the YouTube chat, Nico, has called you absolute encoder fingers.
Encoder.
Yeah. It's another branch we need to register, Scott. Hammertime.
Yes, that's right.
Hammertime. Yes, it's Hammertime. It's Scott said. Yeah.
Yeah, the new national.
I don't know if it's the same
program.
Yeah, I don't know if it's the first time that are in the same time in the GSP, Molly and Nicolas, because it's something that sometimes we start early. The GSP start earlier, and we went later in the second half. And I don't know if Molly
I've been on here with Nicolas before.
Okay.
It was a while ago. Yeah.
One time.
Yes.
Okay.
How many times? Yes, it's the first impression. Like I remember when for me it was the same impression, because I invite to Maxi invite to Nicolas, and when Nicolas started to talk about the time of each exposure. Come on, repeat again. Where is the motors? Where is the go-to?
Yeah, and the funny is that this starts like an accident, because I was trying to get some double stars and maybe a globular cluster, and I said, what can happen if I stack a lot of frames and these things just appear? This is amazing. Well, this is another example. This is the Drift Nebula. This is not a great image, but I really love all the dark spots and the shape and this dust mount down. It's a really nice picture.
Yeah, you got a lot of great the dust lanes, especially in the other detail. I wouldn't say it's not a great picture. I mean, it's for the way you're doing it. I think it's a fabulous picture.
I correct. I love my pictures. I always say
we do too.
The break picture, because you usually read astrophotography and watch images from hours, takes, but
of course we've seen all the amazing, very colorful, and the images that Molly puts out that put everyone's images to shame. But at the same time, scientifically, you've got a lot of the detail that the Trifid offers, and there's so much room for an image like that. And remember, you're using one hand. You're not we're not going with the motors, so you're showing what's possible without, if the budget's tight and you have to choose between bowling equipment and astronomy equipment, you can still do astronomy if you spent all your money on bowling stuff.
Yeah, that's for
sure. There's a technical question here, Nico. Jeff Wise wants to know, how do you plate solve?
Okay. No, the plate solve, you see, if you want to make some astrometry or on that image, I make a few asteroids tried with my dog, but I use a single frames in Astrometrica, and it works. It works. Yes, it works, but maybe as you can't do long exposure takes, you need a place in the sky with a lot of stars. Because if there are tiny stars or a few, it was really hard. So this is another one of Barnard 86, this dark nebula, and was early. Conal was talking about those dark nebulas, and that literally are hiding us what's behind. So I love to watch these dark nebulas when I go to a field or a nice skies. And this was taken in a Bortle 2 skies. It was amazing, and I was with my dogs, and I said, okay, I need to capture this dark nebula. I put my camera and take maybe 20 frames for this picture.
Harold Locke, who's watching on YouTube, wants to know how high do you set the gain or ISO settings on your camera?
Okay. That was a really try and fail and continue, and because when I start, I need to see something on the screen, because the whole sky is moving, but we are moving. So I used to set high gain for be right there, and then drop the gain at the minimum, and just watching one or two stars moving, I know I am there in the right place, and I captured with maybe 1 or 6 gain at most. Because with the short exposures, if you use a lot of gain, you get much noise. It's really hard to process them. So I prefer to use less gain and take a lot of pictures, really a lot, 500 or 700 pictures.
Incredible.
Really
Really
yes, it's
incredible.
something that Nico says is that any times that I try make some deep sky pictures, yes, the gain is need to put in the lowest possible. Yes, it's real, Nicolas. Yes, for every camera, for the 3 H2E, sorry, CWO, we're using now Sibony, and it's the same because the sensors are the similar in the all brands.
The gain helps to bring more detail, but also more noise and more maybe sensor defects. So it's better with less gain and a lot of image stacking. So where I think, okay, where cosmic dust begins, and it's literally and it's impossible not to think about the phrase of Sagan that is, we are stardust. And yes, all the cosmic dust begins in the stars with a mass expulsion or in the explosions of the stars. So I was getting some image of planetary nebulas. I get also with my Dobson. This is the Ant Nebula in Scorpio. This is NGC 6153. This is also near Scorpios. I don't remember exactly the constellation. This is a really nice planetary nebula that you can observe even in a city sky. If you use maybe 100 magnifications, you can watch it. This is one of my favorite planetary nebulas. But, well, as always, my favorite nebula is the Homunculus Nebula in Eta Carinae star, in the nebula of Carina. And I think this is the best images I get with my dog is of the Homunculus star. Is amazing.
That's incredible. You can see the structure.
Yes. When I start getting this, I cannot believe it, because you are in the best sky. You watch in the eyepiece and you see all the Carina Nebula, and the star is so bright. But here in the city sky, if you put a lot of magnification, as you cannot see the whole nebula, you start watching the whole nebula in the star. Is amazing. To observe this is one of my favorite objects. I wait all year for these times where just here, if you wait maybe to 3 or 4 a.m. you can watch this. We have the nebula Carina really high in the sky, so this is my favorite. So okay, this was my presentation, and I really hope you like this.
Yeah, it's very inspirational, Nico. Thank you so much. Thank you. We always love to have you on. It makes I think all of us want to go get a Dobsonian and a camera and just try hand guiding ourselves, to see how well we can do.
Yes, and it's so funny. It's really funny, and I have my equatorial mount, but there is always time I say, okay, this is Dobson night, and I really fun.
Right.
You reach more your optics than the mechanics. It's incredible.
That's right.
Yes, you make honor for opticians. It's great.
Can you imagine the astronomers even in the early 1800s watching Nico work, with his cameras and just pushing a telescope to capture images like that? They wouldn't have believed it, Absolutely. We can't believe it. I mean, it is amazing.
Too cold. Too cold.
I think that we didn't realize that it's amazing. And a few years ago, no one can think of doing this with these cameras.
No.
So Conal says we don't know where we are going on in a few years. The
Right.
technology, we are in the golden age, you say, Scott.
That's the golden age. That's right. That's right.
Thank you.
Jeff Wise wants to change your last name to Nico Dobson. So, all right. Well, up next is César Brolo. César is heads up the optics area of Optica Sirocco in Buenos Aires. And he is a great friend to us here on the Global Star Party, and to many, I'm sure now, thousands of people around the world that have watched him on this program and other things that he does. He has the nickname of 100-mile-per-hour César. He is fearless on his patio and with his cameras and his telescopes, and will take on any celestial challenge. So, César, thanks for coming back on to Global Star Party.
Thank you, Scott. Thank you to everyone. It's a pleasure to be here. Happy New Year for everyone. We are starting the year, the first Global Star Party of the year. Well, tonight I was the sky is cloudy, it's very windy. Of course, that many times in many windy nights, I was watching, I was showing something in my balcony, but maybe I'm too old, sorry, to start in my balcony with a very heavy wind.
Dust. Sorry, we have
to hold you up.
Nice.
Yes, maybe the idea of dust. Yes. This evening was a little dusty with the wind, and the summer storm without rain, only with dust. Well, I am unable to not be able to go to the balcony because I can with these two very light in carbon fiber, maybe they can blow
away.
Blow away and start to fly. But in the last week. While we was talking about many different things, I was taking pictures of open cluster. I say that I don't know which open cluster is. I was more confused if was only an asterism. I thought that this was in the area of the Vela or Carina or the Argonaut especially, but in the night without see the stars and between the buildings, I don't have more reference stars to say, okay, is this cluster? No. Well, but the interesting thing that in the week I returned to the picture that I took in the last with my cell phone in the supplied vacuum. How do you say the name of the small vacuum? The cell phone. The cell. I don't
are you talking about the
small ones have made
back on the back so you can hold the
yes, I don't remember the name of each small. If somebody can help me with the name, well, and I was making pictures of the sky, not in the level of Nicolas, of Nico, of course, but only to make something And let me share screen. If I can show you first the same pictures that I took the last week. Maybe here, sure. Well, this is the telescope in the telescope that I choose to have in home to make practices, because if I have one of these, I can make this the same, that I can tell to the people to make the same, to teach to the kids to make something different. And first of all, the pictures that I took, well, this is the picture with a little of subtract of light pollution, only to see the stars. And I reverse the image like you can found in stellarium, or if you see in the sky the same, only I reverse this. And the last week I told about this asterism here, that you can see that it's like an M letter.
Yes.
Like bomb, yes. M. Okay.
Yes.
Yes. And this is yes. And when I start to found, sorry.
It was my first star cluster that I observed.
M for Molly.
Yes, M for Molly. Excellent.
Molly constellation.
Yeah, yes.
It's
here
the Molly,
you can see,
the Molly asterism. Of course, you have to be in the southern hemisphere to see it, Molly.
I don't mind going down there again.
Bradley. Yes, it's for Molly. Excellent. Our Molly. Okay, you can see the screen here, the map.
Yes.
Okay, here you have the M, because it was not in maybe 5 minutes I started to see in stellarium the how do you say, the globular clusters, the open ones, and I found the M of Molly, and this asterism was excellent to see that this one is the southern Pleiades.
Yes.
And this is the complete exercise. The most important thing with our telescope is watch something and know which object is. And this is magic for the kids or for teenagers, of course, because or people that starting to use the telescope, because the moon, the planets are okay to watch. But when you can say, we can say that, okay, I found this, I took a picture and I know this object is. This was for me was the same object that I understood which one was, and was a open cluster in Norma constellation in the southern skies. For me, at my 16 years old, maybe the first time, because I remember that it was my first time with a telescope that I prepare and I make the lenses. And 16, 17 years old for me was magic to say, okay, this cluster, of course, that only is watching without pictures, and watching in the map, star maps, and say, okay, it's the first time that I understood who I can think, and I can understand that the same that I watching exists in a map, and I can say, okay, this is this cluster, and what's the first one? This is very interesting for me, and something like that last week I couldn't say, okay, I don't know who is this cluster, because in reverse, and say, okay, tonight I can show and I can say, okay, this is the cluster that I found with a telescope without without go-to or, yes. And the idea of this is that, sorry, that I'm using a big screen and I move the pictures of all of us. Now it's in the line of the camera. And sorry. And yeah. And the idea is that when I can make something that says this telescope is okay for that. Okay, I have big field of view with the eyepiece, the position and the distance, the eye relief. It's something that I can teach to the people to use properly, how to use, and have maybe 2 degrees of field in the picture. With 2 degrees of field in a cell phone, you can find everything. You can search a lot of different objects in the sky, and this is why I started to be interested in import a telescope without in inner Barlow lenses, because I like the short focal length, especially for the people that start astronomy. And this is not only something commercial, and maybe for me it's more, it's maybe more hard to explain to the people that the low magnification is a great value. Low magnifications and big field of view. It's great to start to view and take pictures, especially with cell phone. This is the beginning of something, because it was interesting to say last week I took a picture without recognize which object was in the sky, but when you start to watch in Stellarium or another star software, astronomical software, you can see the magic to say, okay, this is the same. This is the M of Molly and or something. They say it's great, and I can't imagine the happiness of a kid making the same.
It's really amazing, Scott.
Yeah. And well, this was my impression with this. Well, of course, I used it last week. I used it in the small one, the Altazimuth mount, not with this, with the Exos 100. Yes, no, I press the button and say, okay, go to
right.
Yeah, but the idea of optics, the idea of open field of view, in an easy idea of Newtonian telescope is really great.
Yes,
and it's great that you can show some objects and you move the telescope, find it with your eye. It's amazing because you found different star colors and you stop to observe and to press attention. It's really
absolutely
nice exercise.
Nicolas. Yes, and first of all, in the F 4.38, it's exactly yes, the F number. Yeah. But I think that is shorter because I need to measure with a focal lens, because this the manufacturer and the designer is really, I think that it have a less millimeters than 50. I think that is more near to 4.3. Maybe Scott, you can maybe check.
I should measure.
Yes, you know that sometimes when you translate the manuals, or maybe it's a little shorter. And I see last week I say that we in the laboratory we put in the focal and only 1 meter, and was less than 1 meter to take the focal test. Well, I need to show you next time,
right?
How it is, or maybe a picture or video when we make the test. Normally we use in the first situations. Normally we test telescopes to be sure that, for example, when we realign a telescope and we assemble again the mirror in the cell of the primary mirror,
sure.
We use this to put the mirror without tensions, without forces that can change the shape of the airy disk. And this is because normally we receive telescopes that have a great geometric shapes of quality, but when we disassemble a telescope to clean or something, every time we are concerned to put again with the Eclipse in this mirror cell,
because you can pinch the glass.
Absolutely, yes. Scott, that this is something that is very important to don't press a lot. Yes, only a little. We see one of these. We know the shade, the shadow of the parabola, and we say how these guys made this parabola for industrial telescope. Yes, it's really, we can watch a great shadow of the parabola. That is not a very when you see in the focal lenses, focal image, the mirror, you can see when it's parabolic. But we can take a measure of this with a diaphragm, a Coude diaphragm. Right. Yeah. Sorry, my pronunciation to the big. I need water, but
it's okay. You're good, César.
It's okay.
Thank you. Thank you.
Thank you.
It comes out of all of us, and yeah, Molly, we found you a new constellation. We are officially calling it the Molly cluster or something.
Yes,
so
completely agree.
César, first discoverer.
I have actually seen the Southern Pleiades when I was in Chile in 2019. Cool. So I've seen it.
Yeah, but did you look at that part of it and call it the see? Now you gotta look at it.
Now you gotta go back.
It has a special.
Gotta go back and look at it.
Gotta go back to Chile.
Yeah.
It's got special significance now. César, you've discovered something new.
Yeah, exactly. And Molly deserved that.
Yes, she does. Absolutely. And this brings up, some comment here that Josh Kovac is saying, I probably need to realign and loosen my primary mirrors. It's very important. You want the best images. You just want if you have a Newtonian telescope, you want to just hold the mirror. You don't want to squeeze it down. You'd be amazed at literally just finger pressure on a mirror can start to pinch the optics. And
yes.
Pinched optics can look triangular. They look
I can say absolutely. I can say something. When I was polishing mirror lenses in my teenager time, many years ago, with a couple of with a friend, we found a little area, because we had something technical that Scott knows absolutely, and many people that polish their own mirror knows. We had a problem with a polishing tool. In the pitch, we had a little depressing, and we we found in the Foucault test, a little mountain. You know, you see
like
in the old, yes.
Yeah.
We thought it made, of course, that we made this without the machine. Earlier, I had the machine, but in this time, we started to make all, and especially the polishing is much better in making in by hand.
Yes.
And we say why we can figure in with the finger.
With just your thumb?
Yes.
Really?
It's really, yes, it's really.
So you put like some polishing
with
on your thumb and
Sodium oxido, yes, and make, of course, making a round.
That is cool.
We make a hole. Cool. We made a hole. Of course, a hole only maybe in 10 times around the mirror, we made a hole. We needed make a press with a paper again and make again a little mountain in the tool to prepare. Not a sorry, a little again a hole in the tool to yes, of course. In 3 hours of polishing more, we found the spheric shape like you need before make the parabolizing, or you told me parabolizing, I think the parabolizing with the mirror a little with the tool, sorry, a little outside the center. Well, I now it's not easy for me to talk. Maybe one time I can show a video from my machine, Draper machine, to the different statement
people
or
would love.
polishing.
They would love to see that.
Yes.
You do that.
But explain the different things when the center carriers, the out of the center, the WB, all Texero stuff.
A lot of technical words to learn in another language. So
yes, Molly, but
just like computers, though, just about anything has its own technical language. So this is another.
This is words because I have my first Texero book, Texero
Gene Texero.
You know that is our Bible. It's our Bible. It's our Bible. Yes, and I have the Texero in Spanish, in French, and in English by Wilman Bell with the last chapters that are beautiful. I remember that I put in my basic computer in the 80s. I remember that I write the lines of the program for basic to make the table the sheet of calculator for the parabolizing mirror, for example. Yes, I don't know. I don't know in which language it's easy for me explain in anyone.
Probably easiest just to show them how it's done,
Yes,
so.
and could be great to show that what we was talking about before about the eclipse that holds the mirror, because many amateur astronomers doesn't know and have problems with the view and say, okay, it's not good collimation, and maybe it's just that detail. So
It's just
showing that it's really important.
Absolutely. I remember that Scott, for example, 3 years ago, start to call to the distributors because they found some mirror with a little of pressure in the first carbon fiber tubes of 20.
It was the Comet Hunter. It was the Comet Hunter.
Yes. Right. But not all manufacturers call to the distributors to say, please check that. And this is something that I love of Sprout Scientific, that they are really optics and They are concerned all about the different process of manufacturing and the control quality. And this is something that in many telescope dealers, they don't know nothing about. They can show you the first telescope.
You are an
in reverse.
unusual.
You never say that. The typical in many stores, window stores, and you say maybe Nicolas, you say that the Newtonian telescope in reverse with the mirror pointing to the sky, because the people
many movies and television shows.
Absolutely, yes, and maybe movies, but if you sell telescope, it works. And so people that show this in their window stores. Yes, come on. It's a new type of telescope.
We get customers who do call and they say, I can't see anything. And we do ask the question, which way is the eyepiece? Or is it down more towards the ground, or is it more up in the sky with your telescope?
Yes.
Well, it's down at the ground where it's supposed to be. We go, no, not on this telescope. This is a Newtonian, and the eyepiece is up high.
Sure. In the 90s, I came to the store in the maybe 90s. Now exists more things about the videos, and the people search more. When teenager that received a telescope like a gift, and he came to the store and showed me the telescope and told me the same that you told me. No, I can say anything, and and I removed this cover. When I told me the cover inside a bag, you show me this cover and have a mirror. Why?
Well, that's
the mirror, of course, totally show with fingers.
Of course, they have to touch the mirror after that.
Please,
right?
give me this. Give me this. Don't touch anymore. I need to clean this.
Yes.
Yes. Sit down, please.
That's how we keep our jobs.
I think what you do is you take the telescope and you hand them a pair of binoculars and you say, start here while we fix your telescope, and and then come to the class. I know it's not intuitive, and when we get back to doing outreach, we're gonna which way do we look, but the joys of actually having someone be able to look at the moon or something through their telescope for the first time is something that I miss seeing, because of we haven't really been able to do much outreach. So hopefully we get back to that.
Mateo Castro is commenting. He says, I've seen sellers put the Barlow lens in the finder bracket. Yes, we have all seen that. So, because what happens is okay, they got to put stuff up online. So they'll build out a telescope. The photographer will go and build the telescope. And a lot of times they have zero idea about how it all works.
Yes. And before YouTube, anything was easy, and many people refused to read the manual. But maybe yes, I remember that we started to write our own manual. Actually, we have one of this, but not for each telescope, because each telescope have the technical things to assemble, But we send actually PDF manual that I wrote in the 90s to talk something about how care a telescope, how your telescope is, and maybe actually in this telescope is nice, the manual, because it's have the things that I think which things in the manual can show to the people. But in the 90s was not really easy. I remember that for any people say, okay, go to the library to and buy a David Levy book.
Yes,
because in this time was the best thing to show to talk to the people, because remember that we don't have cell phones, we don't have only was for me was the David Levy book was the best way to give to the people the idea to have a great maps. And I remember that I found this cumulus, this cluster in Norma with Will Tyrion map, but was not easy. But in the way that David Levy showed the catalog,
yes,
separate, yes, with the sky for south or south or north, and the most visible clusters in the skies or nebulas was the best way to understood the sky for many people. Well, we need to say this to David Levy next Global Star Party to
That's
say
right.
thank you, because it's something that something like I love Cosmos, I love a lot of books, but this book was so important for the people.
Yes.
To really learn about the sky.
That's right.
It's not easy to find a book that show to the people in an easy way to find the things in the sky.
That's right.
We need to say next week too. A
You need to
special
say thank you. Okay.
Yes. Thank you again. Yes, absolutely.
César, thank you very much. Thank you
it's a
so much
pleasure.
for everything.
I need to see a Molly, M of Molly.
That's right. It's so it's now time for Astronomally, and Molly, thank you for coming on to Global Star Party. We love having you on, and we love what you are imaging and how you describe the objects that we're seeing up in the sky, not only with their beauty, but with the science behind it. So thank you very much. I'm going to turn it over to you.
Yeah, thanks, Scott. Happy to be back on again, and excited to know there's an asterism for me now.
Yes, that's right. And another reason to get to the Southern Hemisphere.
Again.
Yeah.
As if you needed one.
Well, first, a bit of happy news. I spent some Christmas money on a new camera.
Whoa.
Congratulations.
Wow, looks like a big one.
Yeah,
congratulations.
Thank you. This thing is enormous. It's so big.
Wow.
You can call it a beer upside down.
This is the ZWO ASI 2600 MC Pro. It's one of their newer color cameras. It's not the full frame one. That's the 6200. Easy to flip those around. This is the APS-C one. So a bigger chip than my 430.
Pretty big chip.
Like a ESPS around.
Amazing.
So this is like a DSLR in size. So bigger than my 294 and my 1600, but smaller than full frame. So this is going to go on my Takahashi, and the 294 that I have now is going to go on my camera lens, my Rokinon camera lens. And one of the big benefits of this over my 294 is, first of all, this is a 16-bit camera where my 294 is 12-bit. So I have a lot higher dynamic range. This one has no amp glow compared to the pretty severe amp glow that's on my 294. And it has extremely low read noise. It's less than an electron of read noise. So
wow,
that's really exciting.
Nice. It's cool, isn't it?
Yeah, it's a cool camera, which is partly why it's so enormous.
Do you even have to do dark frames?
I still do. It's even though it's cool, there's still dark current, and CMOS cameras tend to have a fair amount of dark current.
Okay.
So I still do dark frames. I don't do bias frames though, and I don't do flat darks either, because my flats tend to be very short exposure. Yeah, looking forward to getting that set up. It should be clear next Monday night, so it'll be first light on the new camera.
We're looking forward to seeing what you get. Have you got your target before you get your presentation? Have you picked a target to shoot?
I'm probably actually just going to continue the targets I'm working on now, which is currently I'm doing sharpless. Sorry, let me silence my phone here. Sharpless 2-115, which is a large nebula. Sharpless 2-200, which is a cool looking nebula. The IC443, which is the jellyfish nebula. It's a very popular target among narrowband imagers, and looking forward to doing that with my duo narrowband filter. Let's see, M78 is also on my list, which is a reflection nebula right next to Orion. And I just started, I needed an early morning target, so I just started NGC 2403, which is a galaxy in Camelopardalis, I think. I have to go remember.
I'm trying to think. That's like a,
well,
is
I don't
that
run
the
them
one
all
that
at once.
Camelopardalis. It's hard to say. You know,
I practiced it. I have so many targets because I switch back and forth between the wideband targets like M78 and the narrowband targets, depending on what part of the moon phase we're in. So
doesn't 2403 kind of have a tilt to it like Andromeda? I forget if that's.
I don't think it's not quite as tilted as Andromeda. It's a spiral galaxy that is somewhat tilted, but looking at the subframes I got last night, it's relatively face on, but not completely.
It's a familiar sounding number target. It seems like I tried to go get it years and years ago when I was foolish, but it sounds familiar.
It's not as popular of a galaxy, but it's one of the larger galaxies. I've already imaged a lot of the biggest galaxies because this is my refractor we're talking about. So it's really hard to do springtime targets with the refractor because it's not a whole lot of large galaxies.
All right, it's small, but I think there's some significance to it. I'll have to look it up. I think there's something, I don't know, Cepheid variable that was in it, or
okay. Yeah, I haven't done I usually do my interesting facts lookup when I do the write-up after I finish taking the
well, there's time for that.
Yeah.
But well, carry on. Let me go to me.
All right. I will go ahead and share my screen here and start PowerPoint. All right. That coming through all right?
Yes, ma'am.
All right.
Yes.
Cool. Had to make sure I selected the correct screen. All right. So in the spirit of tonight's topic of cosmic dust, I decided it would be fun to talk about dark nebulae. But instead of talking about a specific one, I decided to kind of cover them as a category because there's not as much to say about any given one. But they're really cool and interesting as an object category. So speaking of the Southern Hemisphere, this picture here in the background is of the Coalsack Nebula, which is a very popular dark nebula in the Southern Hemisphere. And it's kind of right in the kind of main core of the, not the core of the galaxy, but a really bright part of the Milky Way. So it's really easy to see against the background of stars.
Yeah.
So this is the picture I took when I was down in Chile in 2019. So what are dark nebulae? They're also called absorption nebulae because they're made up of dust that absorbs a lot of light. So absorption nebulae. They're also called molecular clouds because they're largely made up of molecules as opposed to atoms of elements like the hydrogen clouds that we see so often in a lot of astro images. It's still a lot of hydrogen, but in this case, instead of being hydrogen atoms, it's molecular hydrogen. So H2, two hydrogen atoms bonded together. There's also a decent amount of carbon monoxide. Hydrogen 2 is actually hard to observe. So we actually look for the carbon monoxide that is usually in the vicinity of the H2 in order to see where these clouds are located. And there's also small amounts of other organic compounds. And there's a lot of interesting organic chemistry that happens in dark nebulae, because you have these organic molecules in a somewhat higher concentration than the rest of space, but a much lower concentration than they typically are on Earth. And that allows for chemical reactions to happen in space that don't happen on Earth, because they're much more they don't interact as often out in space because they're much more sparse. So a lot more interesting interactions can happen out there. And a lot of what radio astronomy does is looking at this organic chemistry that's happening in space, which is really crazy to think about. This picture here in the background is, I can't remember if it's a Hubble image, it might be a Hubble image, of Barnard 68, which is a particularly dark glob of dark nebula that blots out basically all the stars that are behind it.
Yeah.
So where can dark nebulae be found? So the largest concentration of dark nebulae, and where it's also easiest to see it, is above and below and inside of the band of the Milky Way. So that includes both the summer and the winter Milky Way. So Cygnus and Sagittarius are places to find loads and loads of dark nebulae. Even just if you look at the galaxy in a dark sky site, you can see kind of the dark band. And in these pictures, you can see lots of dark nebulae branching off all these dark molecular clouds. In the wintertime, as we're looking outwards from the core of the galaxy, but still looking through the plane of the galaxy, there's a lot of dust between us and the rest of outer space. So that's constellations Orion and Taurus. And in the southern hemisphere, the constellation Carina takes up a lot of a dusty part of the Milky Way, and a lot of dark nebulae can be found in that vicinity. The picture on the bottom of the slide is a dark nebula. Well, it's actually a carbon monoxide map of the plane of the Milky Way, where you can see where a lot of the clumps of dark nebulae are. And the picture in the background is the picture I took at the Texas Star Party. It's a mosaic of 1 minute exposures. And I love this picture a lot. And that's Jupiter up. The really bright thing up over here is Jupiter.
Yeah, beautiful shot.
Sorry?
I had gone on mute. Yeah, that's a beautiful shot.
Thank you.
That's one that I want.
Yeah, so I used a star tracker for that, and just like my 18mm camera lens all the way out. Yeah, just tracked for a minute for 7 panels to make up that image from the hill above the upper field of the Texas Star Party.
Yep, that makes sense.
Yeah. So I wanted to showcase some places to find dark nebulae that, and also an excuse for me to show off more images. So this is a nebula called Cedarblad 214 in the constellation Cepheus. And you can see there's a lot of glowing hydrogen. There's also a lot of dark light absorbing molecular dust. And I included some screenshots from Sky Safari up in the corner to show. So here's like the kind of the wintertime Milky Way, or well, kind of partly, you kind of getting on towards summertime Milky Way down here with Cygnus, but kind of more up here in the winter sky. It's just off the kind of plane of the Milky Way here in the constellation Cepheus. In a similar position, also in Cepheus, is the Iris Nebula, and this is one of my favorite pictures that I've gotten of dark nebula, because I finally got that cool brown color that is difficult to get. This was done at a dark sky site about Bortle 3.5, I think we've determined. So I was able to get some color in the dust there, which was really exciting. Also, another place is in the constellation Taurus, which is a little, quite a fair bit up higher off of the Milky Way, with the Milky Way kind of going along here. But there's this part of the Taurus molecular cloud complex, and this is the Pleiades right here in the middle. Now, I took this picture using my DSLR from a Bortle 5 site, and I was mainly just getting a wide field shot of the Pleiades. But after I did dynamic background subtraction in PixInsight, all this dark nebula came out in the background, and I was completely blown away that I was able to get dark nebula with a DSLR on this was on a like a tracking mount. So I think these were like 60-second exposures and 90-second exposures from Bortle 5 site. I wasn't even at like a real dark sky site here. So it was mind-blowing to be able to pick these out of the background using dynamic background extraction. Then of course we have the Trifid Nebula, which is called the Trifid in part because it has 3 types of nebula. We have emission nebula, the red pink part here, reflection nebula, the blue part, and the dark nebula here going across the middle, like Nico's picture. And so this has all 3 of the major types of nebulae, and it's really kind of right along the main part of the Milky Way here, where there's a whole lot of gas and dust. Although this dark nebula is not in between us and this nebula, it's part of the nebula structure of the Trifid in the constellation Sagittarius. This is one of my other favorite dark nebula pictures. This is from, I think, my first Texas star party in 2017. This is done with a DSLR on a Borg refractor. And this is called the Snake Nebula. And there's also, I don't know if other people call it this, but this portion here, I can't exactly see where I'm pointing because my screen's kind of blocking it. But this looks like a bull to me, like a bull with horns, which seemed fitting for the fact that we were at Prude Ranch out in Texas. Yep. So
just rename it the Corn Nebula. You can do it. The bowl of corn.
So and it's also kind of right up off the main part of the Milky Way in the constellation Ophiuchus here. Now, I just discovered this today when I was looking for that picture of that really dark nebula that I showed on an earlier slide, and I found out that it's actually this nebula right here, right next to the Snake Nebula. And I've been wanting to image that really dark nebula for ever since I first saw it, and I just realized today that I already have, which is really exciting. Yes. You can just see how thick and dark this is, and how it just blots out the light behind it. So that was a fun discovery today.
Makes me wonder, Molly, I mean, if we could fly out there, and go right into the molecular cloud, would we see it at all, or would it be like getting close to a rainbow and you see nothing?
I was wondering that too, and I'm going to answer that question coming up in a couple of slides here, actually.
Okay.
Another place to look for dark nebulae is in other galaxies. It's one of the ways that marks some galaxies as being really cool looking. So like the Needle galaxy here, it's got a really thick, dark bands of dust in its arms, as we're kind of looking on it edge on here. The Sunflower Galaxy, the Black Eye Galaxy, Centaurus A, or the Hamburger Galaxy, they're all really well known for having really dark central bands of dust lanes along their edges. And so that's another place to look for dark nebulae. All right, so some cool facts about dark nebulae. So stars are born in molecular clouds. A lot of the material for stars comes from the material in the molecular clouds, and their much higher density means that those materials can start to coalesce via gravity to start to form stars. A small clump, like a Bok globule, is as much as a light year across, and the larger dark nebulae are hundreds of light years across. So these things look small, but they're enormous clouds of dust and gas. Now, a lot of dark nebulae have densities on the order of 1 to 300 molecules per centimeter cubed. So that's very sparse. So in those nebulae, you might not be able to tell that you're inside of one. And they're quite cold, 7 to 15 Kelvin, which for people who don't speak Kelvin is pretty close to absolute zero. Or if you speak Fahrenheit, negative 447 to negative 432. So very, very cold places in the universe.
but very balmy if you're from Canada. I've been told this.
Yeah.
I thought -11 Fahrenheit was cold and I got laughed at. So yeah.
Oh man.
Anyways, carry on.
Now, to answer your question about whether we could be able to see that we're inside of a dark nebula, Bok globules, which are those little balls of dust that you can see in like the Rosette Nebula and in some other really dense nebula, those kind of densities have 10 to the 5 molecules per centimeter cubed, which is still a lot lower than like atmospheric pressure, but is a pretty significant amount of molecules per centimeter cubed. So I didn't think to run some math on that and see like what kind of like what that might equate to in terms of pressure or like light absorption. But I think at that point you might be able to tell that you're looking through some dust in order to see the stars outside. Yeah, I'd say probably.
You probably have to somehow be, with this many molecules and without. So I and I've, of course, this goes for bright nebula as well. Would you be able to see,
That's a good question. I've heard, like I've read other places that you wouldn't necessarily like be able to see the nebula that you are in because they are quite sparse, at least for like kind of the larger emission nebula. But I'm not sure. I need to find out more definitive. I could probably figure that out by looking at like, I think we have good ideas on what the density of at least common types of emission nebula are. And I could compare that to say like smoke density when you're in somewhere that's smoky and see if there's a comparison to be made there. Yeah, I should do that for a future talk.
Yes.
That would be very interesting because I'm also under the impression, like say you went into a famous nebula like the Orion Nebula, yet if you get too far in it, you don't even know you're there. Where of course the sci-fi movies kind of have you believe you can see it. You can fly in and you kind of see it. So
I think you'd be able to tell from the extinction of the light of like stars of a given magnitude that appear darker. But yeah, I think if you were to fly by one of these nebulae kind of up close enough to where the light would be bright enough to see it naked eye, I think it'd be, from what I understand, too sparse to be able to actually see the light from it, because these things are hundreds of light years across. So by the time you got close enough to see the light brightly enough, you'd be too close to really see it.
Yeah, right.
Yeah. It's a question that many people like me think about. If you fly near in the area of the nebula, how many light and these colors show to you?
I think I can calculate that because we know like the distance of these things. So we know kind of the absolute magnitude of, or we should know the absolute magnitude of of fluence, like the number of photons that are, or flux, I guess, the number of photons that are.
I think you can see the same colors like in a 15 minutes picture, for example, of Orion, very light, very bright, and very strong colors. I think with the naked eye flying in the same area.
Yeah, well, I think we have.
It's my imagination, maybe.
In like the medical community on like how sensitive your eye, like what's the photon flux in order to be able to see light and stuff like that. So
for me, it's an ophthalmologic thing that this is why I think in this.
Yeah,
the sensation, but that you tell us is that we know the level of the magnitude of the area of gas, because it's a fluorescent gas. It's I don't remember the name in English. It's it's not a reflection. It's not a reflection nebula.
Emission. Emission.
It's emission. The gas is, yes, it's like
so we
fluorescent lamp.
We know roughly like what the density of the nebula is, and we know like the wavelength, like the energy that's coming off of this. I think I can calculate like the photons per second coming off of it, and then cool. looking at like spherical divergence and stuff like that, figure out what the photon flux would be at a given distance, and if that's enough to see it.
Yeah, how far away would you actually have to be to see it?
In order to, for instance, to have the Orion Nebula dominate the sky and still see it. And then I would be curious, because with our own eyes, for instance, we can see the Orion Nebula through a telescope, but we don't see color. Whereas you see some color of Orion Nebula, yes, but then you put the sensor on it and all the color shows up.
Yes, I can explain this because I work in ophthalmologic optics. I am not a doctor, of course, but I work every day with glasses and contact lenses, and especially in low vision. That we concern in low vision how the people see the colors. Sorry. You watch the in between green and maybe a little blue, the first colors that you can see but especially Orion. Green of Orion Nebula, because it's the most sensitive color that your cones are. But maybe you have more sensitivity, you can say the red color
so it depends on the actual eyes that you've been given. So
but
I'd have to, next time
we have all the same cones from the same factory.
So I could take like I think there's literature on like what a standard person's like eye response curve is. So I'll get back to y'all on that. How's that sound?
That's good.
It's really interesting about colors.
I'll do a presentation on it at a future show. How's that?
Yeah, and the other question we have is, Molly, are we already in a nebula?
So I from what I know, I don't think that we are. I think that that's something we'd be able to determine with like looking at stars of like the same type in different parts of the sky and stuff like that, and knowing their spectra. I think the understanding is that we're not in a nebula, and that our star was formed in a nebula and moved out of it like stars
moved out or got kicked out of it.
Or got kicked out of it.
Or
we were rejected.
You're not paying rent. Get out of my house.
But for the watching of the landscape, landscape is ridiculous to say in space, but of something that we can view very near to a nebula in a starship, maybe the strong light with color make that we can see as everyone in the starship. It's something red, for example, because I imagine that the light very near to the nebula is so strong, like a picture. Maybe I'm wrong, but thinking fast, I think, okay, near to the nebula, I have I can see this, like, for example, maybe stronger, like polar, how do you say, the pictures that you make, Adrian, I forget the name of the light, northern lights.
The northern lights, yeah.
Northern lights. And maybe I think that is, I don't know, I never see northern lights in a real life, but I don't know if you can see the color.
You can barely see some. Yeah. I had a chance to see it over my head, and I wasn't doing photography at the time. It looked blue to me overhead. Had I put a camera on it, I would have seen all sorts of other colors. Now, when I did see it distant and I took images of it, I could see some of the green, mostly the green, and I could see the movement of the aurora in the distance and the pillars being formed. when I took the shots, however, purples and all other colors showed up with that the sensor was able to pick up. So
maybe it's the most near to imagine if you are near to a nebula.
I think something else to consider too is the when that nebula, the nebula it's emitting some amount of light, and the closer you are, the more spread out across the sky that light is. So it appears dimmer, like how the Helix Nebula appears much dimmer than the Ring Nebula, even though they're roughly the same physical size. It's just the Helix Nebula is much closer and more spread out and diffuse on the sky than the Ring Nebula is. Right. So that's, I think, the kind of the main of like that nearness. Yeah, it increases the number of photons per second, but the number of photons per second is spread out over a larger area. So your eyes are catching fewer of them because it's a much larger thing.
Yeah.
Does it also, and I know we've sort of jumped into your presentation, but it also depend on the wavelength of the light that's coming, because there's only so many wavelengths that we can detect.
Also,
the
we were
visual
saying
spectrum.
versus red and stuff like that with the cones.
Yes, maybe my question is a kid question, because it's something that I could imagine if I can see the complete colors like sci-fi movies, when in the past never you can see in Star Wars, for example, a nebula, but in the new ones they start to show a nebula with very bright colors already but this is real, or the nebulas in a near distance show lower colors and lower brights.
I'll go do some math and I'll do a whole presentation on this. How's that sound?
I think we look forward to seeing that. And I didn't think of it, but
no, it's an excellent question. I get asked it a lot, and now I have a good reason to go actually.
Now you do.
Yeah,
that's right.
Night vision
before we transition to Adrian, Molly, the question was asked quite a while back in chat: is how do you get the best images of dark nebula?
Yeah, so I'm gonna real quick go through what dark nebula look like in other wavelengths, and then I have a how to observe slide like I usually do, and I'll talk about it a little bit there, if that's all right.
Yeah, carry on.
Right.
You have more presentation.
I'll go through the rest of this quickly. So I like to show what these things look like in other wavelengths. So I picked the Horsehead Nebula as an example here. So this is optical, both of these here. The one on the left, they're both my images. The one on the left is in color. The one on the right is with my bigger telescope in just hydrogen alpha. So that's to kind of as a starting point. Looking at it in radio, you can still see the horse head shape, which I think is really cool. And that was actually kind of unexpected, because a lot of times things don't look really the same in other wavelengths. On the right is a pretty famous image from the Hubble Space Telescope of infrared. Now, infrared light can pierce through these dusty clouds. And this was on a near infrared, so you can still see a lot of the dust here. But if you actually go to the far infrared, you can see through these dust clouds. And that's how we look at like the center of the galaxy and stuff like that, looking through all the dust. And unfortunately, I wasn't able to find any images, even in the Aladdin data set, of ultraviolet or gamma ray or X-ray. I guess nobody's really interested in looking at the horse head in those wavelengths. I think it'd be cool. Who knows what's in there, but oh well, nobody else is interested apparently.
We're all interested.
Nobody who has time on an X-ray telescope is interested.
Okay. No, I prefer to ask more questions.
Yes, so observing dark nebula, if you're going to observe them visually, you really need to be at a dark sky site. They're pretty much impossible to see, because you need to see them against you're basically looking for a lack of light. And if that's covered up by light pollution, you're not going to be able to tell the difference. So you need to be somewhere where it's dark and look in places where there are lots of stars, or a nebula, because then you'll be able to see the lack of light where there should be light with a lot of stars or with nebula. photographically, you can do it under sunlight pollution, like the images I showed from Bortle 3.5 and from Bortle 5, especially when it's against the background of a bright nebula. So like the image in the background here is of the Elephant Trunk Nebula, and this is a narrow band, and there's quite a lot of dark nebula showing here because there's some really nice contrast when you do narrowband imaging. There's stuff to see at both small and large fields of view. For visual observing, well, for both of them, you really want a faster focal ratio so you can suck in more light, so you can see where there isn't light for the dark nebulae. And a faster focal ratio photographically will help enhance the contrast as well. So yeah, to photograph it, you really got to, the darker the sky, the better. The picture of the Iris Nebula I took was in Bortle 3.5. The Snake Nebula was in Bortle like 1.5 out of the Texas Star Party. And it's very difficult or impossible. And I hate saying impossible when it comes to things astrophotography, but I think from the city, you're going to be really hard pressed. Except for doing narrowband, of course, then you can kind of see that a lot better. But if you're doing broadband, you really got to be somewhere dark in order to see dark nebula against a broadband background of stars as opposed to narrowband. So I hope that answers your question. And that can be done in color or monochrome cameras. And yeah, finally made it through. Yay, you all are very chatty tonight.
We have a lot of questions about the rank of nebula in the middle of the presentation. Sorry, yeah. Molly, sorry. Yeah.
No, I'll
have a kid question.
I'll put together a presentation on it after I do some math and see what I can find out.
It's a pleasure, really, to you, because it's very interesting.
Yes.
We need that UV sight in southern hemisphere. I know that you went in Chile. Well, it's the same skies, and of course that if you can cross to Argentina, you are welcome.
All right.
Yeah,
we're gonna plan this trip. We're all gonna make a big trip to Argentina and just show up.
Yes, Adrian,
on location.
I consider you. Yes,
you. Yeah,
Adrian
we're here.
Have their own visa, Argentina visa, because we consider to Adrian another Argentinian.
At this point, yes, because I'm usually on with the Argentinians. So, and I've joined the Facebook page, so it's official.
Yeah, yes, and something that I read earlier that was that I don't know in the comments that Scott put that somebody say that their chef ways the Argentinian contingent is astronomically very talented. Well, yes, thank you. Not me. Of course, Maxi and Nico and another one.
Yeah.
But was it when I read this, I said, oh my God, what a lot of pressure for us. Yes, Molly, save us.
You've been delivering. César. Thank you.
Yes.
We all enjoy seeing Southern Hemisphere objects, and we're spoiled to see them from you all on a daily basis because we normally we would have to look them up online or dream of going down there. But you all help us with our ability to see the entire sky.
We live vicariously through.
Yes.
Yeah.
Shorter way of saying what I just said. Thanks, Molly.
Yes.
I'm working on it.
All right, let's move on.
Okay. All right. So up next here is Adrian Bradley. Adrian graces the Global Star Party almost every week with his incredible nightscape photography. And so I did kind of steer the conversation towards dust in the Milky Way. And so we'll see what Adrian is ready to present.
All right, so just straight to it, I'm sharing the screen of an image that I downloaded from the Spitzer Space Telescope. There's a website that this one from the JPL images, Milky Way center aglow with dust. So what I wanted to find was, well, what would you see if you could have the $5 gazillion Spitzer space filter and just blow right through the Milky Way dust? And this is something that has been imaged. I did download this, and you'll see how I tried to use it soon. But what I'll do is just we'll quickly go through. There were a couple of regions that were described on that web page, and the significance to those regions. And so what I wanted to do really quickly was just sort of go through the pair of eyes, which is this this region that they're discussing here, star forming regions that they're able to see once they get rid of the once they cut through the dust with the Spitzer Space Telescope. Molly, you might know this. There's a certain frequency there's a certain wavelength that frequency or wavelength. Okay.
Just divide by the speed of light and you've got the other.
Okay, cool. Well, they're on that frequency in order to see through the dust that normally presents itself here, the center of the Milky Way galaxy. Your image that you had, where you had the kind of the galactic center and the two sides of it, this is essentially that picture. If we could look right through it, there would be the galactic center. These are some other bright star forming regions that are here. What that made me do was wonder, so this is my image that I took of the Milky Way at a Bortle 1 site. So you're seeing some of the nebulosity here, the dark nebula, and I think this dark area here might be that void, or that that dark nebula you were talking about, Molly. The if I'm in the right region in this image that I'd have. But you have the lagoon.
I think it's a lot smaller than you'd be able to see from there.
Okay, so it's lots. Okay, so this isn't that.
Yeah.
Or right here, I thought might be possibly that region, but that's okay. So it's, you can see all of this is blocking us being able to see what the center of the galaxy looks like. What I did, and it may be a little inaccurate because sizing, I don't know if I have it sized properly, but this is what I consider, let's suppose you have the Spitzer filter and you shot at the same region, you'd see a whole lot more data. I aligned where the center, they pointed out where the center of the galaxy was in the Spitzer image, and it's this region, this real bright region here. And I aligned that region with this region, which is considered the center. The sizes may not quite be right because I noticed this little footprint here that might be tracing the cat's paw, but then I have the cat's paw right here. So I might be a little off in my sizing, but this is still, but
you're basically there,
So this is what the
cool.
This is how much more we would see of that real busy part of the galactic center if we had Spitzer vision, or if we bought the real expensive $6 gazillion Spitzer filter. I don't know if there are any filters that work at this wavelength that we could use.
There are, just not like on the commercial market. They're for like research.
Okay, so
there's
it is
that like FLIR, for instance, makes infrared cameras.
Okay, so they can do this. We might not be able to buy it and create a cool picture to look like this and just.
If you have a lot of money to spend.
Okay, so well, when I hit the lottery, I'll make the real image of this, and that's where my money's gonna go, or not. I don't know. I may have to pay some bills. So this is my entry for the as far as dust. If we weren't blocked by our inability to see through all of these dust lanes and things like that, and of course we as humankind we're not, because we have the ability to push our way through it using the right tools. So I thought this made for an interesting look to the Milky Way that we normally see. Also, I was going to discuss the merits of black and white photography, and I can't necessarily tie them to dust other than the fact that you can see dust lanes if you do black and white imaging. You can still see detail in dust lanes. To me, it's similar to doing narrowband imaging with classic astrophotography, and it makes for an interesting look. And the image I wanted to make sure I showed is, let's see, and I'll get to the zodiacal light too, because that also relates to dust. But we'll share this image. Let's see, that goes here. So this is an image where you have Milky Way, and we've seen it, but when doing images like this, where if you want to see through clouds, I think having a dark sky sight to where the light coming from the Milky Way is bright enough to illuminate the picture, you can then do them in black and white, and you can study them, or you can just enjoy seeing what these images look like in black and white. Mm-hmm. And Nico's no longer here, but in Nico's honor, let's talk about the dust from I have had a chance to see the zodiacal light, and this is as the sun is setting. This is around the time of the spring equinox, so the zodiacal light angles this way towards Orion. I think I've discussed it here, but I would wish for Nico to be able to see, and the best times to see these tend to be around the equinoxes or sometime after. And another thing to consider is the amount of zodiacal light, I think, may have increased a bit this year. Study from Juno suggesting that perhaps this is actually dust coming from Mars, and not just the regular, the interplanetary dust or comets or things like that, but this dust is being left by the planet Mars, and they determined it through with Juno flying through it on its way to Jupiter, and realized that the dust traced back towards the orbit of Mars, and then realized this may be coming from, that's where this may be coming from. Right. In the spring, this is where the zodiacal light intersects with the winter side of the Milky Way galaxy. And in the fall, one of my absolute favorite pictures to have taken is when it angles the other way. This time M44 is in the middle of the zodiacal light, and the moon can rise in the middle of the zodiacal light as well. The Pleiades, M45, sits in the middle of the zodiacal light in the spring. So it's interesting, the different, and the fact that it still points toward Orion is also a fact not lost on me as well. So the zodiacal light and Orion, and down here you have Canis Major, and you've got M44 here. Further down here, if I had done this, move this just a little bit to the left, we would have had the moon rising within the zodiacal light. And I do have a picture that I tried to take of that. Do not know what I did with it, but what I'll do is I'll end my presentation on that image. And this shows that from a photography standpoint, dust plays a huge role sometimes in what we image. Let's see if I have it here, and this is not where I have it. Let's see, there we go. It should be in here. Should be. Of course it's not. That's my image of, so there's a horse head, there's a flame. This is a crude but quick image showing that in Bortle 1 skies and with dust on your sensor, there's more dust right here, you can acquire these targets pretty quickly. You can also see the zodiacal light a lot more readily, and obviously my shot of the moon in the zodiacal light may have to wait for another night, but I know it's in here somewhere. And as always, I will end my presentation.
That's nice.
With a bird image, because we know, Scott, you love the bird shots. This is an interesting, the bird's turning in mid-direction. You can see the beak here. And these clouds do look similar to the clouds in the dust of.
Is that a turn?
Yeah, it's in mid-turn. That was its beak. Birds' heads are on a swivel, so their bodies can do this and their heads are directly straight. It's kind of like they've got an uncanny ability to keep their head straight no matter where they're facing, and so they can look at a target and their wings are all over the place. So so at any rate, that's my presentation. We continue to try and in the cold weather, continue to try and do some imaging. Even if I've been experimenting with black and white imaging lately to see if the light of the images and the night sky still carries itself, despite the fact that the colors may not be there. So that's something new to try out and different. In most night sky photography, you won't see a lot of black and white images, but the colors of the night sky are what draw people in. But using the light, maybe you can draw people in just using the light. And then as far as the theme of our global star party with the dust, there's ways of incorporating that dust into pretty pictures, but there's also some scientific meaning behind them as well. And it changes from year to year as this dust is studied. So that's it for my presentation. Thank you all for listening.
Thank you, Adrian.
Thank you. Anytime I can mix birding into astronomy, it's a wonderful time.
Hey, it's all, since everything's made of stardust, and so it's all good. We could somehow mix hamburgers and milkshakes into astronomy. So,
Yes.
So,
absolutely.
Wonderful. Okay.
Excellent.
All right, gentlemen. Well, it has been a great global star party. I have, unfortunately, I have an early morning meeting that I have to attend myself, but I wanted to thank all of you that are still on right now for your great presentations. It was wonderful. Our next global star party will be our 80th. And so we will do we'll give away something special for the next Global Star Party. And
we need all prepare something special. Yeah.
Yes, yes. And so
the 80.
I have some topics in mind right now, but I want to think on it a little bit more. And it probably is going to center around the golden age of astronomy, you know, and so I think that might be a great topic in general, you know. So, all right. Well, and now I want to thank the audience. You know, we have a loyal audience as well, and that's great. It's always fun to see you in the chat and to see you where the conversations go. And I want everybody to know, whether you're a presenter or you're someone in chat, if you're doing something that is for educational outreach to raise awareness about astronomy or telescope use or whatever it is, you know, I'm happy to promote that, you know, to build up what we can do to tell our audience about your programs or whatever it is that you think is important. And because that's what it's all about. We're doing educational outreach, and you know, it's awesome. So thanks again. And at this point, does anyone in the presenters have anything they'd like to add before we close?
Not at all. I think my video is dragging. So in about 5 seconds.
Your eyes are getting full of interstellar dust, and it's time to go to bed. Okay.
That's right.
Yeah.
Absolutely. Thank you.
All right.
I will add this for Nathan, who stayed up to watch, maybe your sister in the background. Keep on with these presentations. We love it. And you know, how you're relating math and solar system to various things. It's wonderful to see. So just keep your imagination going. Can't wait to see what you come up with next. And of course, remember, I'm time lapsed by about 5 seconds because of the way my camera works now. So it looks like a poor audio track, but yeah, keep going. I really do enjoy those presentations. I enjoy everyone's presentations. Khoa, give Karim my regards.
Will do.
And hopefully we'll see him again soon. César, come on. Hopefully the weather will be good next time. And we'll get to see
I need to return to the balcony. Yes, absolutely.
I will say that I did check in recently with the organizers of the Northeast Astronomy Forum, and it's still on at this point. So that would be April 9th and 10th. So anyhow, we'll take care. And Khoa, we're going to have to hear you play guitar sometime. That'll be really cool.
Okay.
Okay.
No pressure.
All
No
right.
pressure.
I have guitars too here. Yeah.
Oh, you do?
We
Do you
can make
play?
a band. Yes, yes, very bad, but okay.
Very bad. Well, I play even worse. Okay, so all right, guys. Thank you so much.
Have a good night. Thank you very much.
Play the radio.
Okay, it's a pleasure.
Good night.
Good night.
Good night to everyone.
Yes. And to all of you in the audience, thanks again. Next Tuesday will be the 80th Global Star Party, and we'll see you then.